All right, guys, welcome back. So we're going to go ahead and continue with our discussion of OSPF. And in this section, we're going to focus on the optimization of OSPF. Specifically, what is passive interface? How can we utilize passive interface? And what would be the effect of utilizing passive interface on OSPF adjacencies? Something that we talked about in our last section. Manipulating the metric for OSPF. Which is much, much simpler than manipulating the metric for EIGRP because there's really only one element that is used in the metric for OSPF, and that is the bandwidth of an interface. Although with OSPF, we do have the ability to adjust the cost manually without changing the bandwidth by setting the cost directly on the interface. We'll talk about default routing, like default information originate, how equal cost multipath load balancing works in OSPF. How do we implement route summarization? Remember we talked about that yesterday. In a multi-area design, one of the benefits that we have is to implement route summarization on an area border router and an autonomous system boundary router, whether we're using the area range command or whether we're using the summary address command. Each of those respectively would be configured on those particular types of routers. What is route filtering? Specifically, what is a distribute list, what is a prefix list, and what are route maps. So these are very good things to discuss, and we'll get into those topics in a lot more detail in the next section as well. I mean, the next class, the advanced routing class. We'll take a look very quickly at OSPF for IPv6, and then how do we use OSPF v3 to combine our dual stack environments by configuring both v6 and v4 using the same transport. That's an interesting concept with OSPF. Not something that typically you would see with like EIGRP. We can certainly run dual stack in EIGRP, but there's a unique benefit to running dual stack in OSPF, and we'll talk about that. And then finally wrap up OSPF by talking about summarization for OSPF specific to IPv6. Okay, so how is the metric calculated in OSPF? It's a very, very simple metric. It is directly related to bandwidth, the bandwidth of the interface, in bits per second, not kilobits per second. Remember, when we're calculating the bandwidth component in EIGRP, it's 10 to the power of 7 divided by the worst bandwidth along the path in kilobits per second. And then we multiply that value times 256. In OSPF, it's 10 to the power of 8 divided by the interface egress bandwidth. Remember, it's always egress interfaces only. We never consider ingress interfaces when we're calculating path metrics. But 10 to the power of 8 divided by the egress bandwidth in bits per second. Which poses a bit of a problem, actually, right? Because if you were to take a look at a fast Ethernet interface as an example, 10 to the power of 8 is essentially how many bits per second a fast Ethernet interface is. So technically speaking, a fast Ethernet interface has a cost of 1. And we can't do fractions with these values, right? We talked about that with EIGRP. We use whole numbers and no floating point math when we're dealing with these values. So that would mean that anything that's fast Ethernet and above would in essence have the same cost. So a gigabit interface, a 10 gig interface, a 40 gig interface, they would all look like they are the same with the default values within OSPF. And that's something that we would definitely have to consider. There is a way that we can manipulate that. We can change the numerator, which is called the reference bandwidth. There's a global command, not a global command, but a global routing command for the global routing process that we can use to modify that reference bandwidth, which is a best practice standard, right? So the metric is relatively simple. We have 3 or 4 routers in a path. All we simply do is look at the egress interfaces and we put the bandwidths of those interfaces into the formula. And if the cost of one link is 10 and the cost of the next link is 5 and the cost of the next link is 5, then the overall path cost is 20. So it's just a cumulative path cost. Very, very simple metric, very easy to manipulate, very easy to understand. So the only issue that we run into is that reference bandwidth. We can actually see on the slide there that the reference bandwidth is listed. The default reference bandwidth is in the blue box, right? 100 megabits per second. And the command that you see there, OSPF reference dash bandwidth, what they're doing in this case is they're modifying it from 100 megabits per second to 10 to the power of 11. So they're going from 10 to the power of 8 to 10 to the power of 11, which then would kind of make more sense for most modern networks, right? Because now my fast Ethernet interfaces are not going to look like gig, they're not going to look like 10 gig and so on. And that's pretty typical actually to set the reference bandwidth to 10 to the power of 11, because if you think about that, that's 3 more powers than what we typically would have, which means that we're accounting for all the way up to 100 gig to differentiate the different speeds, right? So a fast Ethernet interface would no longer have a cost of 1, it would have a cost of 1,000, and a 1 gig interface would have a cost of 100, a 10 gig interface would have a cost of 10, and a 100 gig interface would have a cost of 1. And that should pretty much take care of it, right? You're probably not going to see too many interfaces in your topology that are going to be faster than 100 gig. All right? Most likely this will be something that you guys will end up doing in the lab exercise as well. So like I said, the default reference bandwidth is 10 to the power of 8, which is 100 million, or the equivalent of a fast Ethernet interface. So a 10 meg interface would cost you 10, and a 100 meg interface would cost you 1. And they're just summarizing what I've already told you at this point. So 10 to the power of 11 would be a good, kind of a good reference point. If you don't have anything faster than 10 gig, you don't necessarily have to go up to 10 to the power of 11, but we are seeing it more and more commonly, interfaces that are at least 40 gigs, right? Especially with the Nexus products and some of the data center products, a 40 gig link is pretty common these days. So that's just something to consider. 10 to the power of 11 would certainly take care of that as well. All right. Now, the issue that you run into is the actual speed. And in fact, let me... So I pulled up a capture of a OSPF link state update. The reason that I wanted to pull this up is that I wanted to kind of identify the limitation that we have in the field for representing specific metrics. Unlike EIGRP, where we kind of have a limited field to represent a metric value, the metrics are actually advertised slightly differently in OSPF. There is a limitation with regard to how much data we can store in that field with regard to cost, but I can't recall. I'm trying to think if I could kind of figure it out from here. It's hard to say. Let me see if I should be able to, yeah, this field right here. So we have a 16-bit field, right? If you look at, if you highlight the metric field, we have a 16-bit field that we use to house that metric. Well, that means that 65,535 is the highest you can go. You can't get higher than that because there's just not enough bits to store that information. And that's what they were referencing in the book here. They said that the issue is now for a T1 link, the cost is 64,766. Anything slower than that will have the same cost, 65,535. They don't tell you why, but obviously now you know why, because the field that houses that information is only a 16-bit field. So that's the maximum number that you can represent with a metric. That's what we ran into with EIGRP as well, with the narrow metrics in classic EIGRP. There was an issue with the ability to store more detailed metric information. Does that make sense? So I don't know if that you're going to see, that much disparity between the fastest link in your network versus the slowest link in your network. Very few networks have, very few networks have anything less than 1.544 megabits per second these days. Oh, they do mention it here. They say the 16-bit value in OSPF has a maximum cost of $65,535 for a single link, right? That's one of the differences between EIGRP and OSPF, is that with OSPF, we're not advertising path information. So we don't have to necessarily worry about cumulative costs being represented in a particular link state advertisement. We never represent cumulative cost in a link state advertisement. We simply represent the individual link information in the advertisement. So we would only be concerned about whether or not we're able to represent an appropriate cost for links that are slower than 1.544 megabits per second. So how did the algorithm work? It's literally just a cumulative cost value. Every link is advertising its individual link cost. That's what goes into the link state database. And then the OSPF router that is doing its path selection will simply put itself at the root of the network and say, okay, how much does it cost me to take this path to this destination? And how much does it cost me to take this path? And it will just simply add up the costs along the way. And that will end up being the total path cost for that particular path, right? So this particular link has a cost of 20. Again, it's based on egress only. We don't ever calculate the cost of an ingress port, and so on. So we're just basically trying to figure out what the shortest cost is. Now there's something a little bit different with OSPF that we did not see with EIGRP. And I'm not sure that we'll get into it in a whole lot of detail in this section here, but there's also kind of a hierarchy of which routes we would prefer. So we would prefer intra-area routes over inter-area routes. So that would be my O routes would be preferred over my OIA routes. My type 1s would be preferred over my type 3s. And then my type 3s would be preferred over my external routes. And then there's a hierarchy of external routes. So OE1, OE2, ON1, ON2, and so on. So not only would we, and by the way, cost would not be a factor in that particular case, right? If I have a path to a destination and I've learned about that path internally within the area, and then I have, and we'll say the metric is 100, right? And I learn about this same path through a type 3 LSA, a summary LSA, and that cost is 10, I would still choose the type 1 because the source of information always trumps the metric in the case of OSPF. So we don't have that with EIGRP, right? EIGRP, there aren't different types of routes. There's just internal and external. And administrative distance would be used in that case to differentiate between which route I would choose in that particular case. In OSPF, O routes, which are type 1 routes, are going to be preferred over OIA routes, which are type 3 routes, which would be preferred over OE1 and OE2, which are external type 5 routes, and which would be preferred over ON1 and ON2, which are external type 7 routes. So there's kind of an additional level of complexity when we're doing our path selection in OSPF. All right, so the shortest path algorithm places each router at the root of the tree and then calculates the shortest path to each node. I mentioned this yesterday, right? We're not routing to networks in OSPF. We're routing to nodes. We're routing to nodes in OSPF, meaning that we're routing to router IDs. Because reachability is defined by which router is presenting that network prefix information. So it's always about getting to the node as opposed to getting to the network in OSPF. I mean, ultimately, when we're routing packets, the packets are going to be based on destination IP, which are based on prefixes, but it's always about routing to the node. And you guys got a link to those CCIE videos. You'll learn more about that in those CCIE videos, because I go into a whole lot of detail about what it means to route to a node as opposed to routing to a network. It's a very, very interesting concept. But the overall path calculation is going to be based on that cumulative cost to the destination. Remember, within the area, we're flooding all of the LSAs. Everybody within the area is going to end up having the same topology database. And that's actually absolutely a requirement, right? In order for routers to be converged within the area, they have to share a common database. So every router has a complete picture of the topology, and then based on that, they can make their own decision on how they want to route to a particular destination. Very, very basic concept. So the diagram above represents kind of how R1 views the network. R1 places itself at the root of the network and then starts to calculate reachability information to each of the other nodes within the area, or the other nodes within the topology. And then it will extract from the topology database, the link state database, the appropriate routes based on path cost, and then those are what are going to go into the routing table. So the progression is establish an adjacency, become neighbors, go through the whole extart exchange and loading process to get the database, and then kind of assume that I'm the starting point, and then just start pre-calculating all of the best paths to reach the other nodes in the topology, and then extract the routes from that process. All right. So if R1 was to go down and across and up and over, it would be 20, 30, 45, 20, 30, 44 to reach this network at the top, as opposed to 14 if I took this particular path. So R1 to R3 has a cost of 22 to get to this network. If I want to get to this network over on R4, that's going to be a cost of 20, 30, 40. So R1 to R, and if I went this way, it'd be 10, 20, and 30. So that would be the best path to reach this particular prefix, and so on. It's a very, very simple metric, right? It's not that complicated at all. It's just, calculate the cost of the interface based on the bandwidth, and then simply add up those costs, and that's what the overall path metric becomes. So very, very simple metric. Which statement is correct regarding cost? The cost to reach a distant network from a router is the highest bandwidth of any single link on the path. No, it's cumulative, right? It's not the highest, it's not the lowest. The cost to reach a distant network from a router is the cumulative cost of all the links in the path from the router to the network. That would be the correct response there. The cost to reach a distant network from a router is cumulative bandwidth of all the links on the path from the router to the network. It's related to bandwidth, right? But we don't add up the bandwidth and then put it into the formula. We add up the costs. So each link is going to have its own individual cost, and we add up the cumulative cost, not the cumulative bandwidth. Because remember, it's 10 to the power of 8 divided by bandwidth, and that's what becomes the cost in that particular case. All right, everybody, welcome back. We are now in discovery number 8. In this discovery, we're going to talk about implementing OSPF tuning. We're going to learn how to tune the behavior of OSPF. We're going to start by investigating the network topology. We're going to take a look at the current OSPF configuration, and then we're going to do things like enable passive interface on the distribution routers and the branch routers. We're going to configure some OSPF default routing. We're also going to take a look at equal cost multipath, or ECMP load balancing, and then we're going to take a look at how we can adjust the default and interface cost values in this lesson as well. All right. Now, we've already prepared the devices for this particular presentation. And we have, as you can see here, several different routers. OSPF has already been configured on all 5 routers. And the BR router down at the bottom right there, you can see is advertising 4 external networks into OSPF. So in this exercise, we're going to investigate the OSPF configuration. We're going to configure OSPF passive interfaces. We're going to configure OSPF default routing. And like I said, we're going to take a look at investigating that ECMP load balancing. We're also going to finally take a look at adjusting the OSPF cost calculations. We have 3 areas in this topology. The gateway router, which is the one connected to the internet, has a direct connection to an internet router, 209.165.200.224/27. 226 is the gateway side, and then 225 is the internet side. We've got some loopbacks on each of the interfaces or each of the routers based on their, essentially their router number, if you will. So gateway is router 3, HQ is router 1, HQ2 is router 2, distribution is router 4, and the branch router is router 5 in this particular case. All right. Like I said, all the devices already have their basic configuration in place. All the IP addressing is configured. The host names are configured. And OSPF is already pre-configured in this network. And the branch router is advertising 4 external networks into OSPF, 10.1.1.0/24 all the way up to 10.4.4.0/24 as well. We have some router IDs. We don't have that documented on the diagram here. HQ1 is 1.1.1.1. HQ2 is 2.2.2.2. The gateway router is 3.3.3.3. Distribution router is 4.4.4.4. And the branch router is 5.5.5.5. So let's go into our first task here, which is to basically investigate the OSPF configuration. In step 1 of this activity, we're going to go into the distribution router, and we are going to verify the configuration by first taking a look at the neighbor relationship, show IP OSPF neighbor. We can see that we have 2 neighbor relationships. Router 2, which is router ID 2.2.2.2, is a BDR in this particular topology. The physical IP address of that router is 172.16.24.2, and we're connected to that router on Ethernet 1.1. Router 1, which is 1.1.1.1, that's HQ1, also a BDR, which means in this particular case that most likely we are the DR for those particular segments. If I do a show IP protocols, I can see how we're configured. We have OSPF process ID number 1. We can see that we're routing for networks 172.16.14.24, and the loopback is also included in the OSPF process. And we can also see that we have 3 different information sources in this particular case. Router 5, router 2, and router 1 are acting as information sources. Again, those are the router IDs of those particular destinations. If we take a look at the routing table, show IP route OSPF, we can see that we have several different routes in the topology here. We've got 4 of those external routes. Those are coming in from the branch router. We're learning about those prefixes over 24.2. They have a cost of 20. That's because these are redistributed into OSPF. By default, they're sent in as OE2 routes, which means the metric does not change as you move through the topology. And the default seed metric is 20, and that's what we see in this particular case. All right. Now we have some inter-area routes as well. The 25 subnet coming over from 24.2 as well. We've got the 123.0 subnet, which actually in this particular case we can see that we're load balancing to. We're learning about that via 14.1 and 24.2. If you look at the distribution router, that would kind of make sense. We've got this Ethernet connection that goes this way. We've got this 24 Ethernet connection that goes this way. So we're doing equal cost multipath load balancing over to the 172.16.123.0 subnet. These are ABRs in our topology. HQ1 and HQ2 are ABRs, or area border routers. Gateway router is actually, I guess, technically an ASBR because it is redistributing a default route, or it will be eventually as we kind of go through the process here. And the branch router is also an ASBR because it's redistributing external networks from, well, they're in this particular case, they are just simply connected networks that are loopbacks that we're redistributing. We've also got the 1.1 network, we've got the 2.2 network, we've got the 3.3 network. Notice again, we're load balancing ECMP, cost of 21, equal cost multipath load balancing to that prefix, and then finally the 5.5 prefix. All right, so again, just to refresh, the distribution router has two OSPF neighbors, HQ1, it has a router ID of 1.1.1.1, HQ2 with a router ID of 2.2.2.2, and in this case, they're both BDRs on the segments that are connected to the distribution router. The distribution router happened to be elected as the DR on these two segments because it actually has a router ID of 4.4.4.4. And because we booted everything up essentially at the same time, this router won that election process and became the DR. It also has a default priority. All the routers have a default priority of 1 on their interfaces. So the tiebreaker is going to be that router ID, and the highest always wins. All right, OSPF is enabled on the distribution router for all of those directly connected subnets. If you look at the topology diagram, all of the links in this router are in area 1, the 24 subnet, the 14 subnet, and the 4.4 loopback. The routing table demonstrates that, right? We see those inter-area routes, the 123, the 3.3, the 1.1, the 2.2, as well as the 25.0 and the 5.5. Those are going to come in as inter-area routes. We should have those external routes as well, which we saw, and then we have our OSPF routes. In this case, we're not really going to see any OSPF routes in the routing table because they're all connected subnets. So we don't see any O routes. O routes would be routes that we're learning within the routing domain, if you will. All right. Also make note here that we do not have a gateway of last resort. We do not have a way to reach the internet or other prefix destinations that we may not be aware of. That's going to be something that we're going to resolve a little bit later on. So let's go into the branch router as well. We're going to do a similar thing here. We're going to do a show IP OSPF neighbor. And we'll see here in this particular case that we have a neighbor relationship with HQ2 that has a router ID of 2.2.2.2. HQ2 is the DR on that broadcast segment because we actually set the priority of the branch router, show run interface Ethernet 10. The priority of this interface is 0, which means that in this particular case, this router could never become a DR or a BDR for that particular segment. All right, so it's going to maintain a state of DR other. We would see that if we went over to HQ2 and took a look at that. All right, now it is an autonomous system boundary router because it is redistributing. If I do a show IP OSPF database, I can see that there are some type 5 LSAs coming in from router 5, which is the branch router, 4 different external links that are being advertised. So we know that this is an ASBR because it's redistributing those routes, and it's advertising those routes as type 5 external LSAs because this is an ASBR attached to a normal area, right? They would come in as type 7s if it was an ASBR that was attached to a special area type. This, in fact, happens to be an ASBR attached to a normal area. So these are going to come in as OE2. If I do a show run pipe section OSPF, you can see we're just doing basic redistribution, redistribute the connected networks, including the subnet information, and those would be those loopbacks. So by default, these routes are going to come in as OE2, and they're going to have a default seed metric of 20, which is the default behavior for OSPF. All right, so if we take a look at show IP protocols here, we can see that this router is redistributing external routes from connected, which includes the subnets. This router is in one area. These are the network statements, in essence, that we have to allow the router to participate in area 2. And this is one of my routing information sources. In this particular case, the only routing information source that we have. All right. Now, I shouldn't see the external routes here because I'm the one that's originating those external routes. and they show up in this particular case as connected routes on the router. But we do see all of the inter-area routes. We should have, what, 1, 2, 3, 4, 5, 6, 7, and that's what we have here. The 14 subnet, the 24 subnet, the 123 subnet, the loopbacks 1, 2, 3, and 4, which are the other 4 routers in the topology. All right, so it looks like so far that everything looks to be accurate and represented correctly. Let's go ahead and go into the gateway router, and we're going to do a show IP OSPF neighbor. In this particular case, we have 2 neighbors, router 1, which is HQ1, with a router ID of 1.1.1.1, and HQ2 with a router ID of 2.2.2.2. The gateway router is the DR on this segment with HQ1 and HQ2. So HQ2 is actually represented as the BDR. Remember, we have 3 different routers in a common broadcast domain. So router 1 is only going to form a 2-way state with other DR others. We don't happen to have any in this particular case. So we do see the full state because the gateway router is, in fact, the DR for this particular segment. Now, we should see those external networks here because we're in a different area. Remember, the gateway is in area 0. In this particular case, we do have a default route that is configured that points to 225, which is the internet router. We also have our 4 external routes, again, with a seed metric of 20. Doesn't change no matter where we go within the autonomous system. Now, if we were to change that redistribution statement and, for example, go in and say, okay, let's go ahead and redistribute the connected routes and subnets, but let's set the metric type to type 1, then the cumulative metric for the path cost would be included along with the initial seed metric, in this case would still be 20. All right, we do have some O routes as well. These are the loopbacks on HQ1 and HQ2. O routes are intra-area routes, or type 1 LSAs, and then our OIA routes are our type 3 LSAs. So for router 4, 4's loopback, in this case, which is the distribution router, we can see we're load balancing across router 2 and router 1, which is HQ2 and HQ1. And then for 5.5, we just have a single route to reach that destination. So in essence, what we're doing here is we are making sure that the prefixes that exist in the topology correspond to what we would expect to see in our routing information base. And actually, this is exactly what we've confirmed. Right? The routing table shows that we're learning those external routes, which are advertised by the branch router. The gateway is using the path through HQ2 to reach those external networks because that's the best path. All the other routes are inter-area or intra-area routes, are O routes, and inter-area routes, which are OIA routes. And those come from area 0, area 1, and area 2, respectively. So our next task in kind of tuning this topology, if you will, is to go ahead and set up passive interface. Now, in our lecture series, we discussed passive interface as an important concept in not only adding efficiency to the OSPF implementation, but also adding a security element, right? If there are no peers on a particular segment, whether it's an Ethernet LAN segment or a serial link, which would typically have a peer, but maybe it's an external link to a service provider, or maybe it's a couple of different subnets. We want to suppress OSPF from running on those particular interfaces. And we can't suppress the protocol by simply disabling OSPF, by not including network statements for those particular prefixes. Because if we do that, then those prefixes don't get advertised. And that's a really, really important concept. We have to have network statements to include the networks that we want to advertise, even if those particular interfaces are not running the protocol. Or I should say, don't need to run the protocol because there are no peers that would hear that information. So passive interface is a way for us to reduce the amount of resources that the router is utilizing. It suppresses the hello packets. In addition, it will ignore essentially any rogue or untrusted hello packets that might come in on a particular interface. And because it suppresses both the inbound and the outbound OSPF packets on the interface. All right. We're talking about hardening the protocol, right? We want to harden the routing protocol. We want to reduce the amount of CPU utilization that is necessary for the protocol to operate. We want to reduce the amount of bandwidth, so passive interface is a way for us to do that. Now we could do this two different ways. We could do passive interface default, which would make all of the interfaces passive, and then we could specify the individual interfaces that we don't want to be passive, or we could just simply explicitly identify the interfaces that we want to make passive. Now, technically, we don't really have any LANs in this particular topology, particularly any host-based LANs. So we're going to assume that the loopback interfaces are the ones that we're going to make passive in this particular case. Those loopback interfaces are there to kind of simulate those local connections or those LAN connections that we might have. We certainly don't want to run passive interface on all of these peer-to-peer links, because if we were to enable passive interface on those links, then adjacencies couldn't form between those particular peers. All right. So on the distribution router, we're going to go ahead and set the loopback interface. Let me close this guy out. We don't need two of these. On the distribution router, let's go ahead and go into router OSPF 1. Why did it turn off? And we are going to go ahead and make our loopback interface passive by simply typing passive interface loopback 0. Now, if I was to go to my branch router, we can do this a different way. I could go into router OSPF 1. And I could simply say passive interface default. Now this will bring down the neighbor relationship that we have with our peer because we've actually suppressed the hello protocol on all of the interfaces. And then I could simply come in and say no passive interface Ethernet 1.0, and that adjacency would reform. Keep in mind that there's really no difference between these implementation methods. It's just a matter of how many interfaces you have are going to be passive and how many interfaces are not going to be passive. If you've got 10 interfaces that are passive and one that's not, passive interface default would be the option, and then explicitly enable no passive interface on the one that's not. If you have 10 interfaces that are not passive and only one that's passive, then you would do the opposite. But the idea here is that we're not really, in this particular case, doing anything different. It's just a matter of interpretation and a matter of implementation. So let's go ahead and do our show IP protocols. We can now see that loopback 0 is configured in this particular case as a passive interface. If I do the same thing on the branch router, in this particular case, I would see a little bit different output because I would see all of these interfaces are passive. We don't see anything that says that an interface is specifically not passive, but obviously Ethernet 1.0 would be included in that. And then we have all these other interfaces that this particular router has in this case. All right. We can also, we would see possibly maybe some other interfaces like a voice over IP null 0 interface and so on, but not in this particular router platform. All right. So passive interface has been configured for the distribution router on loopback 0 and for all of the interfaces on the branch except for Ethernet 1.0. If I want to go ahead and just re-verify that I have my neighbor relationship, show IP OSPF neighbor, and I can see that I still have my full adjacency with 25.2, which is HQ2 in this particular case. We did reestablish that. We saw that pop up here as soon as we made that interface not passive. We saw that adjacency come back up right away. Okay? Now, one of the things that we want to kind of consider as part of this configuration is how do we handle default routing? And that's what our next task is. We're going to take a look at default routing. How do we configure OSPF default routing? And then we're going to take a look at the ECMP equal cost multipath load balancing in this particular case. So the first activity is to just talk about OSPF default routing. To be able to perform routing from our OSPF domain to the internet or to some sort of external network, we have to either know all the destinations that we're trying to reach, or we have to have some sort of default route. Now we can inject a default route, and we talked about this as part of our lecture, by using the default information originate command. Now, wherever we execute that particular command, whether it's on the gateway router in our particular topology or some other router in the topology, that is going to start injecting, that device that we execute the command on is going to start sending in a default route as an OE2 type 5 route, which makes that device a ASBR. The default route gives us the most scalable approach as far as routing to destinations that we're not familiar with. It guarantees smaller routing tables. We know that fewer resources are going to be consumed on the routers. There's no need to kind of recalculate the SPF algorithm if one or more of the networks fail in the topology and so on. It's kind of like a very general summary, if you will, in this particular case. Now, to implement default routing in OSPF, we inject that default route using a type 5 LSA. And we do this by executing the default information originate command on whichever ASBR, in our case it's going to be the gateway router, that has a connection to that public domain or that internet domain. That ASBR is now going to generate a default route using a type 5 external LSA, all right? Which means that all of the standard concepts of type 5 LSAs, where they can go, where they can be sent, not into any special area type, into the backbone area, into normal areas, is going to apply in this case, right? So we're not going to inject that type 5 route in any kind of special area type at all right? We implement this by using that default information originate command, and then we connect that gateway to our external network. So if I go to my gateway router, which in this case is the router that is connected to the external domain, and I go into router OSPF1, and I say default dash information originate with a question mark, I have several different options here. One of the options that I have is to go ahead and use the always keyword. Now, if I was just to hit carriage return at this point right now, this gateway router would inject the default route, but only if it has a valid default route itself. And we do in this particular case, we have a static default route configured on this router. If I use the always keyword, that's going to inject the type 5 LSA as a default route into the OSPF domain, even if it doesn't have its own valid default route. Because we may have some static routes that go to some external prefixes we still want to have reachability to. We don't necessarily have to have a default route. The other option we have is to go ahead and specify a seed metric if I want to specify the OSPF cost for the route. In the case of default information originate, the default seed metric is a cost of 1, but I can override that with this particular behavior. I could specify the metric type. Is it going to come in as an external type 1 or is it going to come in as an external type 2? I can also apply different set and match conditions, like setting a tag for the route or setting a metric or metric type by applying a route map to the configuration as well. So we can advertise the quad 0/0 route into the OSPF domain by just simply saying default information originate. And that's what we're going to do in this particular case. If I use the different keywords, of course, I can modify the behavior of this particular command. Now, the router automatically becomes an ASBR in this particular case. In fact, if I come into the gateway router and I do a show IP OSPF database self-originate, you can see that I am now generating a quad 0 type 5 LSA, all right, which indicates that, in fact, this is a default route that's being injected into OSPF as a type 5 LSA. So that makes this router in essence, a ASBR. Now, if I do a show IP route, pipe include quad 0, you can see that we do have a static default route that points to 225 in this case. And if I try to ping that external network, 209.165.201.1, it is reachable. All right, so because we put in the default information originate, we know that we're originating that type 5 LSA. I can also do a show IP OSPF, and I can see a couple of different things here. Number one, this particular router is redistributing external routes, which makes it an autonomous system boundary router. Now it says here redistributing external routes from, and normally we would see something like connected or summary or EIGRP or BGP or whatever. Because we use the default information originate command, it doesn't show up in this particular case. All right. Now, if I go to my distribution router now and I do a show IP route, I can see that we now have a external OE2 route with a default cost of 1. That's our external route. If I look at the route in detail, show IP route quad 0, I can see that it has a seed metric of 1. It is a default candidate. That's what the asterisk here represents, that it's a candidate default route. Now, interestingly enough, we see the forwarding metric is 20. What does that mean? If the metric of the route is 1, what does this forwarding metric represent? If you recall, in OSPF, it's all about routing to nodes, not networks. I am learning about this quad 0 default route through a type 5 LSA, but I'm not routing using that type 5 LSA. I'm using a route to get to my ASBR, my ABR, which in this case is HQ1 and HQ2, and then to get from the ABR over to the external router. So there's actually kind of a three-step recursion process here. If I do a show IP OSPF database, and I look at this quad 0 route, it says, okay, the advertising router is 3.3.3.3. Now, I don't have a relationship with 3.3.3.3. This is a type 5 LSA, and it doesn't describe reachability to 3.3.3.3. It describes reachability to this external network. Okay? So what do I use to reach 3.3.3.3? I use a type 4 LSA, and that's what this represents here. This is a type 4 LSA, which describes reachability to my ASBR, right? My ASBR in this case is 3.3.3.3, and the advertising router is 1.1.1.1, which is my ABR, okay? Now I actually use my type 1 LSAs, my router link states, to reach the ABR. So this is the way that I reach the ABR, this is the way that I reach the ASBR, and this is the way that I reach the external network. It's all about routing to nodes, not to networks per se. Yes, we're learning about networks and prefixes, but we're trying to do recursion and route network layer reachability through the different LSA types that describe how to reach the different nodes in the topology. So again, if I look at this route, it is an external type 2. It has a forwarding metric of 20, which is in essence the metric to get to the ABR, and then the metric to get from the ABR to the ASBR in area 0. That's the overall path cost. So even though the seed metric is 1, we can still kind of identify what the best way to go is. In this particular case, we're load balancing between 24.2 and 14.1 to reach that external prefix. All right. And if I do a show IP route on BR, in this case, it's just going to show a single path to 25.2. All right. Now, if I do my pings and my trace routes, these are going to work just fine. I go ahead and do my ping to 209.165.201.1, and that works fine there. Do the same thing here, 209.165.201.1, and we can ping there. I can also do a trace route to 209.165.201.1, and I'm going to go ahead and do just a probe count of 8 in this case, just to generate some extra traffic. So there's the 8 ICMP echo requests. Here are the 8 ICMP echo requests for each of these destinations. But you can see that we're actually load sharing, or load balancing, I should say, between 14.1 and 14.2 in this particular case. If I do my trace route on the branch router, let's just copy this here. If I do my trace route on the branch router, you can see that we're just basically sending the traffic over a single path. All right. Now, what happens if I delete the default route on the gateway router? Let's say no IP route 0.0.0.0, 0.0.0.0, and I put in the external or next hop 165.200.225. And if I do a show IP OSPF database external, you can see that the max age value has been met. We're actually poisoning that route in essence, and we're deleting that route from the database because I didn't use the always keyword. I didn't use the always keyword because I don't have a specific gateway of last resort set on this gateway. Then the route is not going to be advertised. If I do a show IP route here, I can see that the gateway of last resort is not set there. If I do a show IP route here, I can see the gateway of last resort is not set there. Now I can still ping the destination, right? I could still ping the 192.168.201 destination because we have a static route. In fact, let's do that. If I come in here and I ping 209.165.201.1, well, we can't reach that destination here. Well, because we don't have a gateway of last resort. Now, if I look at the gateway router, do show IP route static, I can see that I actually have a static route here to 209.165.201.1. Here's the thing though, there is no default route on this router. So you might think, okay, well, if I go ahead and just come in here to router OSPF 1 and I say default dash information originate always, yes, it's going to inject a default route into the distribution router. Show IP route, we can see now that we have a route to that external destination again, quad 0 route. And in the branch show IP route, we have a route to the external prefix, quad 0 route. And now if I do my ping 209.165.201.1, I can reach that destination. So this is kind of an interesting use case scenario, if you will. I don't necessarily want to route all the traffic to the internet, but I want all the other routers in the OSPF domain to send their basically their default traffic to the gateway router, and then based on whatever policies or static routes or whatever kind of routing I have configured on the gateway, then I'm going to allow that routing information or those routes to be reached, but not necessarily all the routes because we don't have a specifically defined default route on the gateway router. Does that make sense? All right. Basically, the ASBR in this case, the gateway router, has a pre-configured static route to reach that specific host on the internet. So we're going to take a look at our last section here, which is OSPF cost. Now, cost is an interesting thing with OSPF. Each router within the OSPF topology has to determine its own best path based on the network topology. And the shortest path first algorithm calculates those best paths based on whatever the lowest metric is or the lowest cost is. Now, if the RFC actually specifies that cost is an arbitrary value. It doesn't have to be bandwidth. Each vendor can choose to implement cost however they choose. They can calculate it whatever formula they choose to use. They can use bandwidth, they can use delay, they can use other values to calculate path cost. In the case of Cisco IOS, though, we use the bandwidth. All right, specifically the formula is a reference bandwidth, which by default is 100 megabits per second, or in powers of 2 math, that's 10 to the power of 8, divided by whatever the interface bandwidth is. So I guess the question is, how can I influence the path cost? Well, there's two ways to do it. You can either change the cost by changing the bandwidth of the interface, or you can change the cost by setting the cost manually on the interface. So when the shortest path first algorithm tries to determine the best path towards the destination, it looks at all of the total costs for the specific path, it compares the costs against different paths, and then the path with the lowest overall path cost gets selected as the best path. The OSPF cost is really supposed to be just an indication of the amount of overhead that's required to use a particular path. Like I said, the formula is reference bandwidth, by default 10 to the power of 8, divided by interface bandwidth. Now this is a 16-bit value. It's an integer that goes from anywhere from 1 to 65,535. The lowest value would typically win, and again the reference bandwidth is 100 megabits per second by default. So on high bandwidth links, so if I have a link that's 100 meg or more, the automatic cost calculation doesn't work anymore, because it basically results in the cost being equal to 1 for everything that's fast Ethernet and above. 10 to the power of 8 divided by 100 is 1. 10 to the power of 8 divided by 1,000 is 1. Well, not technically, but we average up to the lowest, or the closest integer, if you will, because we can't do decimals and so on. So a 64K link typically is going to have a cost of about 1,562. A T1 link, if I do the math, 10 to the power of 8 divided by the speed, 1544000, that's going to be 64. There's no floating point math on these calculations, so we just drop the remainder and the cost simply becomes 64. All right. So again, the metric is relevant, but here's another very, very important concept. The metric is only relevant on the egress. In other words, ingress values do not affect the overall path metric. Only the egress values of the interfaces affect the path metric. I'm going to demonstrate something about that a little bit later on. All right, and Dijkstra's algorithm basically just simply determines the cost by adding up the link cost along the path. So if I come in here, actually let's do this before we make any changes. Let me do a show interface Ethernet 1.0. You can see that the bandwidth of this interface is 10,000 kilobits per second, which is 10 megabits per second. If I look at 1.1, it's also going to have a bandwidth of 10,000 kilobits per second. And if I do a show IP OSPF interface Ethernet 1.0, we can see that the actual cost calculated for the interface is 10. Same thing for 1.1. If I look at loopback 0, for example, we should see that the cost is 1. Right here, where is it? Right here. Cost is 1 because the bandwidth is much higher than 100 megabits per second. All right, so again, anything that's fast Ethernet above, gigabit Ethernet, 10 gig Ethernet, they're going to have a cost of 1. Basically, that means that the default reference bandwidth is far too low for common link types today. The solution is to go ahead and change that reference bandwidth. So let's make sure all my prompts are the same here. And because 100 megabits per second is really not that practical these days, typically we want to adjust the reference bandwidth to at least support up to 10 gig links. You can certainly go higher than that. I'm going to talk a little bit about why that's something you need to be careful as well with as well. So we simply go into our router. I'm going to do all the routers in this particular case at once. Yep, we're good there. I don't need the internet router. And what I'm going to do is I'm just going to go into config T, router OSPF 1, and I'm going to say auto-cost reference-bandwidth, and 100 would be the default. This would account for gig interfaces, and then this would account for 10 gig interfaces. I'll send that configuration. All right, you do want to make sure that you're consistent and you apply the reference bandwidth across all of your routers. It's not a value that has to match between the routers in order for them to form a peering adjacency, but you will run into a situation where you may have some asymmetric routing, or you may have suboptimal routing that's going to occur if you don't set that reference bandwidth to be the same on all of the interfaces, or excuse me, all of the OSPF processes. So now if I go back to my distribution router, show IP OSPF interface Ethernet 1.0, you can see that we've changed our cost by a factor of 100 on that interface. The same thing with 1.1. And if we look at our loopback interface in this case, oops, we can actually see the cost is still 1 here, but if I do a show interface loopback 0, you can see that the bandwidth is pretty high, right? It's just an arbitrary value that gets set. Not arbitrary, but not certainly calculated. It's a loopback interface. All right. I can even see that the cost is reflected in the routing table. So if I look, for example, at the 3.3 route, you can see that we've increased the metric from 20 to 2001 in this particular case, which is a factor of 100. All right. Now we are load balancing to this destination, right? We're using 24.2 and we're using 14.1 as our paths. They both have the same metric. So if I do a show IP route, I can see in this particular case for that 192.168 3.3 subnet, we are load balancing across the link between 2 and 4 and between 1 and 4, HQ1 and HQ2 in this particular case. What if I want to change that behavior? What if I said, you know what, I want to use Ethernet 1.0 as my primary path. This path right here, I want that to be my primary path to reach that external prefix. Well, I could simply come into my interface and change the cost, IP OSPF cost, and simply make it a lower cost. Again, egress values matter in this case. So I'm only affecting traffic flow in one direction by setting this cost. But now if I do a show IP route, you can see that I'm no longer load balancing to that destination. I'm using this cost of 1501, which makes sense, a cost of 500, plus whatever the other costs are, which would be 1,000, and a cost of 1 for the loopback. The loopback itself is going to have a cost of 1. The Ethernet interface, which would normally have a cost of 10, because we're multiplying by a factor of 100, is going to have a cost of 1,000. And then the added 500 that we set gives us a total path cost of 1501. There is an inherent problem with what we've done here, though, right? We can see that the metric did definitely change. However, if I go to my gateway router and I say show IP route 192.168.4.4, which is the loopback on the distribution router, you can see that I am actually still load balancing. So in one direction, I am using a single path to reach the gateway loopback, but in the other direction, I'm using both paths to reach this destination 4.4. That's because we only set the cost on this particular interface. If I were to go to set the cost on this interface to be the same, then we would have symmetric routing. So it's something to be very aware of as you're manipulating these routes, after you're doing your what we would refer to as traffic engineering for OSPF, basically. Make sure that you're applying a consistent configuration. All right? Now, there's certainly a lot of other things that we could talk about with this topology. There's a lot of things we could take a look at. But this is the conclusion of this exercise within the ENCOR scope of the class. So we're going to wrap up this lesson, this exercise, this demonstration. We got another lesson, couple lessons that we're going to go through. We also have another couple of discoveries that we're going to be running through. So we'll see you guys in the next section. So the next thing we'll talk about is summarization, right? Remember, there's two types of routers that we can summarize on, ABRs and ASBRs. On the ABR, we use something called the area range command, which allows us to summarize routes into our type 1 routes from one area into another area as type 3s. And on the ASBR, we use the summary address command. It's really important that you understand how summaries work, because in modern networks, it's very important that you kind of incorporate that as part of your design if you have the appropriate addressing scheme and you can aggregate these routes effectively. In order to effectively summarize routes, it's extremely important that you plan out your addressing scheme appropriately so that you have contiguous blocks of addresses throughout your areas. Otherwise, summarization is going to be pretty much impossible. What is the benefit of doing a summary? Well, let me demonstrate real quick, okay? Since I already have this exercise here, let me summarize these prefixes, these loopbacks into the rest of this OSPF topology. So, did it reset already? Dang it. It reset. Sorry, the battery's died on my microphone. What I was saying is that I generated that summary, which the best summary I could do was a block of 8 addresses. We only had 4 networks that were advertised as external networks, but because of the way the networks were created, I had to summarize them as a /21 to include the 4, right? Because it has to go from 0 to 7, not from 0 to 3. If it was just the 0 to 3, I could have summarized them as a block of 4 addresses, but I had to do a block of 8. Now the problem is HQ1 now believes that it can get to 10.1.7 and 10.1.6 and 10.1.5, even though those networks don't exist. So whenever you generate a summary, and this is EIGRP, it's OSPF, whenever you generate a summary through some sort of dynamic process, a corresponding null zero route gets created on the router that's generating the summary. And this is for loop avoidance so that the 10.1.7 and the 10.1.6 and the 10.1.5 networks end up matching this null zero route, which means those packets get dropped. It wouldn't be particularly a problem on this router anyway because we don't have a gateway of last resort. But if I had a gateway of last resort and I didn't have the null zero route, when somebody sent a packet to 10.1.7 or 10.1.7, then this router would probably end up using its default route to try to route that, and then we might get a loop or it might just continue to get routed when it's not supposed to be routed. So that null zero route gets created. Now, the other component to this is that how do I define the metric for the summary? Well, we can see that it came in as an OE2 route on HQ1, just like any other type of external type 5 route, so the default seed metric was 20. We can manipulate that just like we always do with OSPF. We can make that summary go in as a type 1 or as a type 2, OE1 or OE2, I should say. We can specify the seed metric. We could actually use a route map and do some sort of tagging as well, because I can come into my branch router and let me get into the branch router here. Config T, router OSPF 1. Oops. Can't see what I'm typing. Router OSPF 1. All right, and when I do my summary address command, I did 10.1.0.0. 10.1.0.0 with a, let me change my screen size here. It's a pain in the butt. And I'm doing a, let's set this to, let's go a little bit bigger. So let's do a summary address 10.1.0.0, 255.255.248.0, and you'll notice that I have some options here. I can tag the route. It doesn't allow me to modify the metric type or specify a seed metric. The only way that I could do something like that would be to implement some sort of route map and redistribution to be able to send those routes in, and then I would be limited on what I can summarize anyway, right? So we are doing the redistribution. The summary is going to take whatever we're doing with the redistribution. So if I said redistribute connected subnets metric type 1, and then I did my summary. Well, I believe the summary is already there, but I'll throw it in here again anyway. So the summary is just summarizing those routes. If I go to HQ, I should see those as OE1 routes in this case, right? So it's the actual redistribution that controls how the route is inserted, but the summary is still going to allow those routes to be summarized. It's interesting that 2 and 3 and 4 are still showing up separate. We're seeing the 1, but we're seeing the 2, the 3, and the 4. I might have mistyped something, but you get the idea, right? Yeah, I should. It's interesting that it's not suppressing those individual routes. 248 should be correct in the third octet. Interesting. Have to play around with that a little bit. All right. But that's how we summarize on an ASBR. On an ABR, we summarize by using the area range command. All right. So let's say, let me see if there's actually a prefix that we can summarize. I mean, I guess I can just kind of go into distribution and create one. Well, I'd have to do it on HQ1 or HQ2. So let's do, let's go to HQ1, and I'm going to summarize from HQ1. I'm going to summarize those loopback interfaces. So if I do a show IP route OSPF, I should have several different O routes. So 2.2, 3.3, and 4.4. Let's say I wanted to summarize those into area 1. So the 2.2, the 3.3, and the 4.4, going back to the diagram here, we actually don't think we have a diagram on this slide. But we know where those exist, right? 2.2 is the loop back here. 3.3 is the loop back here. 1.1 is the loop back here. So I wouldn't be able to include 4 because 4 is in this area. But let's say I just wanted to summarize 2.2 and 3.3. All right. Main thing is I just want you to I want to show you how the summary works on an ABR. All right. So let's say I go into config T. I'm just going to change this to 100%. really annoying. Router OSPF 1. And instead of using summary address, which I would use on an ASBR, I use the area range command. Area range, area, let's do area 0 range. So this is the point that I wanted to make for you guys. The area that you're specifying in the area range command for the summary is the area that you're summarizing from, not the area that you're summarizing to. So, you know, I'm taking the area 0 routes and I'm summarizing them into area 1, but I wouldn't put a 1 because the area that I'm specifying in the range command is the networks from area 0, not into area 1. And I want to do the 192.168, 2.0, 255, 255, 254.0. That would summarize those 2 loopbacks, the 2 and the 3 loopbacks. Right? So now if I go to my distribution router, I should see an OIA route for that particular summary. And it's right here. Does that make sense? So that's those 2 loopbacks. Normally I would be seeing the 2.2 and the 3.3. They're still coming in as 2.2 and 3.3, by the way, because we have 2 HQ routers. That's another thing to be kind of cognizant of. This is from HQ2 and this is from HQ1 because I didn't do the summary on HQ2. We're seeing the individual routes on HQ from HQ2 and the summary route from HQ1. All right, you guys understand the benefit of the summary. Makes sense, right? We're trying to reduce the size of our routing table. We're trying to ensure that if there is a topology change in a particular area, that topology change does not have to be propagated to the rest of the domain. Because the summary doesn't change if one of the routes in the summary goes away, if that makes sense. All right? Only summarized routes get advertised. So that limits the topology change reconvergence to the area that the summaries are coming from. In other words, the type 1 LSAs within the area. All right, so we're going to reduce the size of LSA flooding, or the size of our databases. We're going to reduce the LSA flooding. We're going to reduce the CPU load, etc. Okay? Which 2 statements regarding OSPF route summarization are true? ABRs summarize as type 5s, negative. They summarize as type 3s. ASBRs summarize as type 2s, negative. They summarize as type 5s. So ABRs summarize as type 3s, which by the way is always the case. ABRs only generate type 3s outside of their area, from one area to another. They'll generate type 1s and 2s possibly within their area, but they generate type 3s going to other areas. And ASBRs summarize to type 5s. Which 2 options play key roles in route summarization? Network numbers and areas should be assigned contiguously. Absolutely. In order for us to have effective summarization, we have to have contiguous blocks of addresses. Otherwise, our summaries just cannot be concise enough, and they might be too generic. We might get some suboptimal routing. I have no idea what FLSM is, but we're doing variable link subnet masking for sure, and we're not doing first hop redundancy. So FLSM and HSRP have nothing to do with it, but yes, you want to have those contiguous blocks because you might end up summarizing, a particular group of networks from one router, and then summarizing those group of networks from another router, and because they overlap, you might get some suboptimal routing. All right. All right, so we're going to move into our next section here, OSPF route filtering tools. It's interesting that they kind of classify these as OSPF route filtering tools because these are tools that you can actually use to provide filtering and policy-based decisions for any protocol, actually. It's not just limited to OSPF. Certainly they can be applied to OSPF, but prefix lists and access lists and distribute lists and route maps can be used pretty much for just any protocol, as well as many other processes on the device to do, manipulation of all kinds of things. It could be for QoS policies, it could be for routing policy propagation, etc. But nonetheless, we'll still talk about these with regard to OSPF, and we'll have you guys do a discovery on this. And then we'll finish up the day by talking about OSPF v3 and doing a discovery for that, and then move on. All right. So there are many ways that we can kind of control how neighbors share information. As of right now, when you have two devices that become neighbors, whether it's EIGRP or OSPF or BGP, well, BGP is slightly different. We'll leave that one out for now. But whether it's OSPF or EIGRP or RIP, if two routers become peers, if they become neighbors, they pretty much automatically share everything that they know, right? And that may be something that you want to limit. You may not want to automatically share everything you know with a neighbor or a peer. So we can control that in several different ways, right? And depending on which method you choose will depend on what kind of flexibility you have in controlling what information gets propagated to a peer. One of the ways that we have is to use something called a distribute list for route filtering. And a distribute list will allow us the ability to either specify what we send out to a peer or what we allow to come into a peer. And it's not, again, we're not necessarily protecting against routed traffic. We're protecting against the dissemination and the propagation of routing traffic. So we're actually applying a distribute list as a filter. Applying a distribute list as a filter to either apply what routes or prefixes we share with a peer or what routes or prefixes we receive from a peer. So we have in this first example here an access list. It's a standard ACL. We don't need to use an extended ACL in this case because we are literally filtering on source information. So a standard ACL is always used to filter on source. And the source in this case is, of course, the routing information. We're denying the 192.168.4.0 network, essentially. So maybe a 4.0/24 prefix or anything that starts with 192.168.4. So it could be various subnets, it could be an entire network or whatever. We're permitting everything else. And if you look at how this is applied, we can kind of identify what the overall objective is. We go under router OSPF 1 and we say distribute list 1, which is referencing the access list, not the process ID, the access list that we just created, and we say in. So what this is basically saying is, hey, any peer that I have in OSPF, it doesn't matter which one it is, I am going to filter out the 4 routes from coming in from those particular peers. Very, very simple way of kind of limiting the prefixes that come into the database, even though we may have a full adjacency with that particular neighbor. All right, they're still advertising it, right? We're not instructing them to stop advertising it. So the link state updates and the link state advertisements still include the 4 subnet. We're just filtering it out as it comes in, and we process that information. All right. Now, the problem with a classic access list is that it doesn't take into effect the subnet mask, right? And it also doesn't take into effect other aspects of the traffic itself. We're applying this access list to the OSPF process. We're not applying this access list to a particular interface or a particular host. So that's what the purpose of a distribute list is to allow us to filter traffic coming into the router from a neighbor. There are other ways that we could actually identify not only just a blanket network, like all the 4.x subnets, but we could also apply a filter that would say, okay, all the 4.x subnets that have a subnet mask of /28 or more, something to that effect. In order for us to do that, we need to use something called the prefix list. Before we get into that, though, let's just wrap up this section here. When we apply the distribute list, there's three ways we can apply it. We can apply it in the outbound direction, we can apply it in the inbound direction, or we can apply it to a redistribution process. So we could actually say, and by the way, that could be either outbound or inbound as well. So we could say, apply a distribute list to a redistribution process from EIGRP to OSPF, or from BGP to EIGRP, or whatever it might be. All right. Again, the limitation, though, is that we're matching prefix information. We're not matching specifically prefix length. We don't have an option in an access list to specify anything about the subnet mask itself. So, in order for us to be able to do something like that, we would have to use a prefix list for filtering. So, prefix lists get created just like an access list in global configuration mode. Those prefix lists are sequentially numbered. We don't have to apply the sequence number. The sequence number will be applied automatically as we enter the access list, but we give the prefix list a name. In this case, the prefix list name is PFL, and then we specify whether or not we're going to permit or deny specific prefixes. But the way the prefix list is written will identify not only the prefix itself, but will identify the subnet mask. And there's a couple of ways that you can do this. You can specify it as you see on the slide here without an operator, right? Operators would include things like greater than or equal to, or less than or equal to. There's a couple of other ones as well, but in this particular case, we don't see the operators specified in the list. So what we're matching in this particular case, this permit, is the specific route of 10.10.11.0 with the subnet mask of /24. We're not using that mask, that prefix length. We're not using that to say, okay, well, we're just going to match the first 24 bits. We are literally saying we're going to permit this exact route, to whatever the policies apply to. It could be a route map. It could be a, some sort of redistribution process or whatever. But in this case, instead of just matching on the IP address, the 10.10.11, we're also saying, and the subnet mask has to be a /24. The second example is permitting the 10.10.12.0 /24 network as well. All right. Now it says in the callout box above, it says we can indicate that the subnet mask must be in a specific range. Well, if you had an operator, that would be true. If we had an operator like LE or GE for less than or equal to or greater than or equal to, that would be true. We are calling out a specific range in that case. In this case, we're not, because it's an exact match. And I'll probably go through a couple of different examples here in Notepad just to describe kind of how these prefix lists work, because a lot of people tend to get confused about the operators and how they technically work when we're doing our match conditions. All right. So as the text says here, compared to an access list, a prefix list offers better performance because it can filter based on the prefix itself, which an access list does, and the prefix length, which an access list doesn't do. IP prefix filters were implemented with the IP access list that were configured with the distribute list command. That's the previous example that we saw. But an IP access list that's used as a route filter has several different drawbacks. The subnet mask cannot be matched. Access lists are evaluated sequentially for every IP prefix in the routing update, and extended access lists can be cumbersome to configure. You don't really need them either. There's really no reason to match with an extended access list if all you're doing is filtering routes. But if you did choose to use an extended ACL, it could be a little bit more complex. The prefix list command, as we've mentioned already, has some significant advantages over an access list command because the idea is that we have the ability to match on a subnet mask. All right. What the router does is it takes that prefix list and it transforms that list into a tree structure. And each branch of the tree serves as a test against whatever it is that we're filtering. We determine the verdict of either each of the permit or deny statements much faster than if we were to sequentially compare packets against an access list. So they're much more efficient to process. Not only do they provide us more flexibility and control on prefix specifics and prefix length, but also in the way that they're processed, they're much more efficient. All right, so we could put a sequence number in the prefix list so that allows us to sort the statements. If I wanted to add an entry later on, or if I wanted to remove an entry specifically. But those sequence numbers are applied automatically when you generate the list anyway. It's kind of like if you add existing lines to an extended ACL on a router, it's just simply going to start incrementing sequence numbers for those lines for you automatically. And you can modify that access list based on those sequence numbers. All right. So routers can actually match networks in the routing update against the list. We could say, for example, the 10.0.0.0/16, which would match the 10.0 routes, but not the 10.1 routes. Keep in mind, in the case of 10.0.0.0/16, without an operator, it would actually match specifically the 10.0.0.0/16 route. It's kind of like if I said prefix list PFL permit 0.0.0.0/0. That would match the default route, specifically the default route. Because you would, if you interpret it the way they've written it here, you might say, well, the /0 means I don't care what any of the bits are, so that would match any route. That's actually not true. With an operator, you could do that, but without an operator, it's an exact match. Okay? I don't know if they give us any kind of examples here, but if they don't, I'll go through. Yeah, they don't really give us some examples. So let me go through and do a couple of different examples here in Notepad. Because I want to make sure that you guys understand the benefit of having these prefix lists and what kind of capabilities we have with match conditions on these prefix lists. So let's say, for example, I did a permit, and I'm not going to write the whole prefix list, but I'll just kind of write the permit or deny. And I did a permit of 0.0.0.0/0. Well, this would be matching a default route, right? If I did a permit of 0.0.0.0/0 with a GE32, so GE stands for greater than or equal to. What am I matching in this particular case? Any ideas at all? In this particular case, I'm matching host routes, right? So when you use an operator like GE or LE, excuse me, this changes. The meaning of this slash notation changes. When you're not using an operator, we're just basically matching the exact route. But when you're using an operator, this /0 now indicates how many bits in this address I'm matching against. So in this case, I don't care about any of the bits in the prefix. I'm really just kind of matching the subnet mask. So this is matching all host routes, if that makes sense. All right. if I did a deny, for example, of 128.0.0.0/1, and I said LE 8, right? In this case, we are denying all Class A networks, right? In this case, I'm saying, okay, the match condition is 128.0.0.0, which means the first bit in the first octet is turned on. The /1 indicates that I'm matching against that bit, so any route that has that bit set, right, is going to be denied. Actually, I mistyped that. Let me change what I said here. So I'm saying that any bit that has that, or network that has that bit turned on. And if I change this, actually, let me make it kind of more realistic. Let's do GE8, right? That's actually what I intended to do. Is I'm saying, okay, anything but Class A, right? So any Class A network is not going to have that first bit set because the Class A range is from 0 to 127, which means that first bit would be turned off. That means that we're not matching that first condition in the prefix list, right? A 127 network wouldn't match, a 126, a 125, a 10, a 15, whatever it might be. With the GE8, we're saying that the subnet mask would have to be greater than or equal to /8. So this could, in this case, we could be saying that we're permitting all Class A subnets, and we're also filtering out anything beyond Class A if the subnet mask is 8 bits or more. So a 128.0.0.0/8 would get filtered, and any 128 subnets would get filtered. Does that make sense? So 128.10.10.10/16 would, or sorry, 128.10.0.0/16 would be filtered. 192.168.0.0/16 would be filtered, and so on. So you have a little bit more flexibility in what you can do here. Let's say, let me do a couple more examples because I didn't do a very good job of explaining that one. Let's try, what if we said we wanted to deny all, thinking about how I want to do this. Let's say I wanted to deny all odd subnets. All odd subnets. I'm probably making it more complicated than I need to. Let me think about this a second. So if I did 192.168 0.0 slash let's do 23. I'm thinking if that would be the first 23 bits that we're matching against. So yeah, that's not going to work in this case. Let me just do kind of one that would be a little bit more practical, right? So let's say, for example, I said permit 10.10.0.0/16. This is going to be pretty common type of one. And I said LE24. Oops, 24. All right. What is it that we're matching in this particular case? Now, a lot of people, when they look at this, they'll just say, okay, well, it's any 10.10 subnet with a subnet mask from /16 to /24. And that's, I guess, technically true, but that's not how the prefix list is written and it's supposed to be interpreted. The /16 indicates how many bits in the prefix that we're matching against. So it is any 10.10 network. And then the second argument, the LE24, says as long as the network in question has a subnet mask of 24 bits or less. right? So a /28, a 10.10.0.0/28 would be denied. A 10.10.0.0/30 would be denied, but a 10.10.0.0/24 would be permitted. Does that make sense? The reason why I distinguish that is because if I said GE24, then you might say, well, how is that a range from 16 to 24? Because it can't be, right? Now we're not specifying a range. We're saying, okay, the first 16 bits have to be 10.10, but now the subnet mask has to be larger than 24. Or it has to be equal to or larger than 24. So a 10.10.0.0/18 would not match. A 10.10.0.0/18 matches the first condition, which is the first 16 bits are 10.10, but it doesn't match the second condition, which is the mask has to be 24 bits or more. Does that make sense? So there's kind of a lot of different ways that you can interpret these prefix lists, and it's not just a matter of just specifying a range or a specific host of addresses. Let me see real quick if we can pull up some examples online as well. All right, so I found this page here. It does go through a couple of different examples, and I think once we go through this, I think you guys have a pretty good understanding of what we're talking about here. Again, the syntax is IP prefix list, give it a name, specify a deny or permit, specify the network prefix and the length, greater than or equal to or less than or equal to. Those are the options that we have for the operands. All right, so again, if I do not specify a GE or an LE, then it's an exact match. All right, so in this case, this particular prefix list is matching this exact prefix in the routing update or the routing information or whatever it is, however we're applying that in that environment. Here's an example where they have an LE32. So we're saying, okay, this is the prefix 0.0.0.0. This is the number of bits that I'm comparing against in the prefix. So I don't care about what the bits are. None of the bits matter. And the subnet mask has to be less than or equal to 32. Well, guess what? This prefix list is kind of like a permit all, isn't it? Because every single route is going to have that condition. Every route in our topology is going to have a mask of 32 bits or less. So this is the permit all prefix list, if you will. Okay? The first 0 bits of the prefix list are checked, and then the subnet mask must be equal to or less than 32. This again is an exact match. If I want to block just a specific prefix, I just don't use an operator. And then there is also a implicit deny at the end. So you would have, say, if I wanted to block this prefix, but I wanted to allow all other prefixes, I would go ahead and put this prefix in place, right, to permit the remaining prefixes, in the list. So you could also include the first one to say GE32 or GE24 or LE24, which is basically like saying 24 exactly. But it's not really necessary in this particular case, because if I don't specify an operator, then it assumes that it's an exact match. So this would be an example of a default route. Let's say I want to permit all prefixes that start with 10.0, but the mask is less than or equal to 30. Very simple. 10.0.0.0/16 LE30. So the first check is that the first 16 bits of the prefix need to be 10.0, and then the subnet mask needs to be less than or equal to 30 in this case. All right. So a 10.0.0.0 would not would match in this case. A 10.10 would not match because the first 16 bits are not the same. A 10.0/30, 10.0.10.128/30 would match because the first 16 bits are 10.0 and the mask is less than or equal to 30. A 10.0.0.10/32 would not match because the /32 doesn't meet this condition here. All right, so only the first and the third prefixes would be permitted. Permit all prefixes in the 192.168.0.0/24 range with a mask between 26 and 30 bits. So this is where we're saying, okay, match the first 24 bits of the prefix, 192.168.0. Make sure that the subnet mask is 26 bits or greater and less than or equal to 30. So that gives us our range of subnet mask bits. This prefix doesn't match because the first 24 bits are not 128 or 192.168.0. This prefix does match because it falls, the first 24 bits are the same and it falls within the scope of the prefixes. 192.168.0.0 matches the first condition, which is that technically, I guess, the first 24 bits match, but the subnet mask falls out of the range. And same with this one. Subnet mask falls out of the range. Deny all of the loopback interfaces with a /32. All right, so basically it's, hey, deny any network that has a mask of GE32 or LE32. In this case, I would say that GE32 is all you need. You don't actually technically need the LE32 because if you add the LE32, it doesn't really do anything in this case, right? I'm trying to think why they did that specifically. I understand why they put the permit after, right? Because the permit after is going to permit everything else that has a prefix of less than or equal to 32. And remember, these prefix lists are processed in sequential order. But I don't think you would need the LE32 in that particular case. We would just say any host route, basically. Now, there's no way to specifically match a loopback. We would have to assume that all of our loopbacks are 32 bits and there's no other network that's being presented that's 32 bits. If that were the case, we would have to put some specific permits in place to permit those other networks first and then deny the rest of them. All right? Anyway, I think you guys get the idea. There's a lot of flexibility with these in the matching conditions. Just keep in mind that when you are using the operators, that it changes the behavior of the prefix list itself. Okay? All right. What are two benefits of using prefix lists rather than access lists? Prefix lists give you better performance. That is true. Prefix lists allow you to control routing based on the source and destination IP address. That's not true. Prefix lists enable you to control metric types. Not true. We would have to do route maps for that. A sequence number feature is an exclusive feature of prefix lists. That's not true either because access lists have sequence numbers. Prefix lists enable you to match routes in part of an address space with a subnet mask that is longer or shorter than a set number. Yes, that is true. All right. Any questions about that before we get into the route map discussion? What is a route map? Route maps are excellent tools to be able to manipulate all kinds of things. All right. Now we're going to talk about this in the context of routing itself, which is where route maps are mostly going to be used. But we can use it for both routed traffic or we can use them for routing traffic. So I can use a route map to do something called policy-based routing. In other words, I could say, okay, take all my HTTP traffic and set the next hop for that traffic to this address, and then allow all my other traffic to route as it normally would be routed. So that's a policy-based routing example. So we're using a route map to override whatever the default routing behavior might be in this particular case. But we can also use route maps to manipulate traffic that's being, routing information that's being processed back and forth between routers. I can use route maps to set BGP attributes. I can use route maps to set OSPF and EIGRP metrics, metric types. I can use route maps to manipulate which routes get redistributed, which routes don't get redistributed. So I have lots and lots of options with a route map. And route maps are basically a lot more flexible as well, because not only do they allow us to match on specific conditions, but route maps allow us to set conditions. This is the first time that we've seen something where it provides us the ability to actually set something, not just match something. So I could say, okay, I want all of these external prefixes that are being redistributed to have a metric type of 1 and to have a seed metric of 100. So I'm matching the routes, and then I'm also able to set the routes in this particular case. So this very colorful chart here kind of describes some of the benefits of a route map. Route maps will work like access lists, but they're much more sophisticated because we have match conditions and set conditions that we can use. They offer top-down processing, so very much like an access list or a prefix list, an access list specifically, they can be processed from the top down. When I have a set of clauses when I create my route map, and each set of clause statements has a set of match conditions and a set of set conditions. We don't always have to do match conditions. We don't always have to do set conditions, but they could have both. Those clauses are going to be processed from the top down. And as soon as we find a match, we stop processing the route map. So that we have a sequential list of clauses that are processed. And as soon as a clause matches a particular packet, we apply whatever policy is established within that clause, and then we stop processing the packet. We name our route maps, we don't number them. And we have match criteria and set criteria using if-then logic. So I could say, if this, do this. If this, do this. If the prefix is this, set the metric to this. And you can actually reference access lists from a route map. You can reference prefix lists from a route map. You can reference all kinds of filters from a route map, so that you can apply different set conditions to whatever you're matching against those different policies. All right. I will, if the lab exercise doesn't allow us to kind of go into more detail, I will provide you guys some more detail after the discovery or during our review of the discovery to show you some different examples of what you can do with a route map. It's very, very interesting. What kind of applications can we use these route maps for? Filtering during redistribution or even distribution of routes between peers, policy-based routing. Like I said, I can override my default routing policy by matching specific packets and saying, okay, take this packet and send it this way, or take this packet and send it that way. I remember in the old route test, there was a lab on the old route test where you had to take your HTTP traffic and you had to send your HTTP traffic to one interface and then have all the other traffic get routed as it normally would be. And the way that you did that is with a route map. So that was a pretty interesting exercise that you had to do. Undoubtedly, we're going to see this stuff in the advanced routing course as well. The other thing, and probably one of the most common places you're going to see route maps, is for BGP policy adjustments, allowing us to either impose or modify BGP attributes for prefixes that are being shared between BGP peers, and for establishing both inbound and outbound BGP policies. So a very, very interesting and highly flexible way of controlling information. So as you can see from the graphic here, a route map is a sequence of clauses, not just individual lines, but a sequence of clauses, which are sequenced by their number. The 10, the 20, the 30, those are the sequence numbers. They have a route map name, which in this case is my route map, and each clause has a permit or deny. So that's an interesting concept as well. Typically with a deny, well, it depends on how it's applied, right? If I'm applying a route map to, say, redistribution, A deny in a clause would indicate that I'm denying that those prefixes from being redistributed. Does that make sense? Permit would say I'm allowing those prefixes to be redistributed. But it really just depends on where the route map is applied. The route map itself can include a set of match statements, match the interface that the packet, the route came from, match an access list, like an extended ACL that matches the traffic flow, for example, like for HTTP traffic, match a prefix list that matches routes that might be advertised from an OSPF peer, whatever it might be, right? And then our set conditions allow us to set variables, set a route tag, set a metric, set an exit interface or next hop, all kinds of set conditions that we can do. And again, once we get into the discovery and we start going through the discovery, I'll show you guys some different examples there. All right. But this is the route map. Each line is sequenced. We process them from the top down. And we can add sequences in between if we need to, as long as there's enough space to add a sequence in between. So if we had a 10 and a 20, we could add a 15 in the middle if we chose to modify the route map. And there's an implicit deny at the end, right? So again, keep that in mind. If the route map doesn't explicitly permit something, it will deny something. That's not necessarily a bad thing. Just keep in mind based on what it's applied to. So for that example that says, okay, I'm going to apply a route map as a policy on an interface to say HTTP traffic gets routed this way and the rest of the traffic gets routed normally. I don't care about the implicit deny because the route map's purpose is to override default routing behavior. So the implicit deny at the end is not to say don't route the traffic. The implicit deny at the end is to say don't policy route the traffic, right? So it's a little bit different than an access list in that regard because we're just simply not overriding the routing policy. When you're writing the match statements, there's a couple of ways that you can do it. If the match statements are, if the match conditions are included in the same line, like you see on the slide here, match IP address ACL1, ACL2, ACL3. That's a match or condition. If the packet matches ACL1 or ACL2 or ACL3, then we would go ahead and do whatever the route map states. If the match statements are entered sequentially in individual lines, that's AND logic. So I can say match IP address ACL1, enter, match IP precedence, whatever, whatever conditions I'm matching, right? As long as those match statements are entered in individual lines, that's a Boolean AND logic, and that means that all of those conditions have to match before I decide to apply the particular route map policy. So here's an example where we're saying match IP address ACL1 and match interface FA00 and match metric 3. Okay? So just keep that in mind as well when you're doing these conditions, when you're doing these match conditions. All right? So again, the sequence number allows us to identify how these route maps are processed in order and so on. You define the route map globally. You define your match actions. You define your set actions. Again, not every route map clause is going to have a match action. For example, I might have a 3-clause route map and the first 2 clauses match something and set something. But the last clause does not have a match condition, it just has a set condition. What's happening in that case? Basically, in that case, we're saying whatever's left over, do this, right? We're not matching anything specifically. So a route map clause that doesn't have a specific match condition would match anything. All right? We also may have route map clauses that have match conditions but don't have set conditions. Typically, those are going to be deny clauses. So if it's a redistribution process and I want to deny specific prefixes from being redistributed, I would simply match those prefixes. There's nothing to set because it would be a deny clause, which is basically saying deny redistribution. So not every route map clause requires a match condition or a set condition. It just depends on what you're trying to achieve. All right. So a couple of other things here. You need to consider these steps when creating a route map. First, you must define the route map conditions. Optionally, you can provide an action to be taken when the condition is matched, and then finally apply the route map to whatever it is. It could be redistribution, it could be an interface, a policy on an interface, or whatever. The sequence number argument works as follows. If you have no entry, if no entry is defined with the supplied tag, the entry is created and the sequence number argument is set to 10. Assuming it's the first clause in the list, that would be the case. If only one entry is defined with a supplied tag, that entry becomes the default entry for the following route map command. The sequence number argument of this entry is unchanged, meaning that you could build a route map and you could start at sequence 50 if you wanted to. And that would be the sequence number that you would start with, since you put that in explicitly when you configure the route map. If more than one entry is defined with the supplied tag, an error message is printed indicating that the sequence number argument is required. I think they mean to say without a supplied tag, but yes, once you've started creating a route map, you do have to sequence the additional clauses that you're entering into that route map statement. So you may not have to apply a sequence number to the initial clause, but for the additional clauses, you're going to have to apply a particular sequence number. If no route map tag command is specified with no sequence number, the whole route map is deleted. Meaning that if I say no route map, my route map, then it deletes the entire route map. It's kind of like saying no IP access list extended, my access list. So we're not deleting an individual clause, we're deleting the entire route map. Set commands are used within the route map to modify criteria. How are multiple match criteria in the same line of a route map processed? Is it a logical and, a logical or, a Boolean if, a logical if? It's going to be a logical or, right? One or the other or the other. That's specific there. Okay, so we will get you guys into this next discovery, and we'll talk about it after you're done, and then we'll move on to our final section of this chapter. All right, everybody, welcome back. We are now moving into our second discovery of this section here, discovery number 9. In this discovery, we're going to talk about applying OSPF optimization. We're going to take a look at optimizing by first implementing things like route summarization on our area border routers and our autonomous system boundary routers. We're going to also take a look at the impact that summarization has on the OSPF database and on the internal routing process. And then we're finally going to take a look at what do we do with specific filtering options. We're going to take a look at applying some route filtering on our ABR, which in this case is router 1, and our ASBR, which is router 3, and so on. So we're going to take a look at ABR route summarization. We're going to take a look at ASBR route summarization. And then finally in this section here, we're going to take a look at some different OSPF filtering options. Now we have a pretty basic design here, multi-area OSPF design that includes 3 different areas. Area 0 with router 4 as an ASBR connected to the internet, and router 1 as our ABR. Area 1 with basically just an Ethernet WAN, simulated WAN link. Router 2 is an internal router in that area. Router 1 is the ABR. And then finally router 3, which is also an ASBR in area 2. And that's going to be sending in these external prefixes in this particular topology. We have a prefix on the internet, 192.0.2.0, and then we have a link, a point-to-point link from the ISP to router 4, which is the 198.51.100.0 subnet. All right? Now, all the devices have their basic configuration in this particular case, including their host names, their IP addresses. Router 1 through router 4 are also already pre-configured with their OSPF configurations. We do have some static routing as well that's used to reach the internet networks specifically the 192.0.2.0 subnet. And then router 3 is advertising those 4 external networks into the topology. Now, one thing we don't see in the diagram here is that we have several different loopback addresses on router 2 as well. 192.168.16 all the way through 192.168.23. Those are going to be some simulated LAN networks that we're going to end up summarizing. And then we have our simulated LAN external networks, 33.4 through 33.7 on router 3. Those are also part of our loopback configuration. Now, in OSPF, there's only 2 different types of routers that we can summarize on. An area border router, which in this case is router 1, and an autonomous system boundary router. Summarization on the ABR is done by using the area range command, specifically area. Then we specify the area ID from which we're summarizing, not to which we're summarizing. So if I have a whole bunch of loopbacks on router 2 here, which we do, and I want to summarize those loopbacks into the domain, I would say area 1, area 1 range, and then I would specify the destination prefix. I could specify the address and the mask. I could say advertise or do not advertise. If I want to suppress that advertisement, I can also specify the cost value. All right, now that means that these type 1 and type 2 LSAs that are being generated inside this area are going to get summarized on R1 into the other 2 areas that R1 is connected to. All right, because again, we're not specifying the area to which we're summarizing. We're specifying the area from which we're summarizing. And those are going to be generated as type 3 summary LSAs. The summary route is only going to get advertised if we have at least 1 individual prefix that falls within that summary range. Also, and this is important to note, the cost of that summary route will have the cost of the prefix that's included in the summary range that has the lowest cost. So if I've got 20 different LAN interfaces that I'm including in my summary, whichever one has the lowest cost, that becomes the initial seed metric for that particular route. In addition, for the summary route, I should say. In addition, the ABR is going to create a null 0 route that corresponds to that summary, and that's a loop avoidance mechanism. I'll talk a little bit more about that as we kind of go through the process of configuration. So the first step would be, let's just go ahead and go into router 1, and let's make sure that router 1 has the appropriate prefixes. So I'm just going to do a quick show IP route, and I should see those external networks. There's those 4 external networks that are coming over from router 3. 33.4, 33.5, 33.6, and 7. And then I see all of the OSPF routes. These are all the routes that are coming from Area 1, which are being advertised through 12.2 primarily, right? The 16, 17, 18, 19, 20, 21, 22, and 23 subnets are being summarized. So, or we will eventually summarize those particular prefixes. So it's important to note that before you actually go in and do the area range command and before you configure your summary, make sure that the prefixes exist first, because I'm only going to summarize routes that exist in my routing information base. I will not generate a summary if the summary does not include at least 1 prefix in my routing information base that falls within that summary range. So we do see the loopback interfaces, which are all the /24s. We see the 8 Class C networks that are advertised from router 2. These are coming in as intra-area routes. We know that they're intra-area routes because they have an O in front of them. We also see those the 4 external routes from R3 and so on. We're also in this particular case receiving a default route from router 4 in this topology as well. So, and that's coming in as an OE2 route, which tells me that that's already a redistributed route, whether it's default information originate or whether it's a redistribute connected. Now I can actually tell the difference here, because if it was redistribute connected or redistribute static, the seed metric would be 20. Now I can't guarantee that, right? Because we can obviously override whatever that default seed metric is going to be during the redistribution process if we wanted to. I can kind of infer, though, that this is done using the default information originate because I can assume that maybe we're not adjusting that seed metric, and that's happens to be the default seed metric for the default information originate. But nonetheless, we still do see that default route in the routing table. Now, if I go to router 4, I should see a bunch of inter-area routes. Show IP route. And in this case, we'll look at our OSPF routes. And we can see those inter-area routes meaning coming from other areas. So these are my type 3s. These are ultimately the routes that I'm trying to remove by doing the summaries, right? We can see the same external networks as well. Those come in as our type 5 LSAs. And again, we're going to be looking to summarize these external routes as well to make the database more efficient and so on. So let's take a look at the database on router 4. And we should see similar outputs here, right? Show IP OSPF database. And we should see in this particular case, here are the type 3 LSAs in the database. The ABR is the one that's advertising those particular prefixes. And we also see our type 5 LSAs. In this case, we also see our type 4 LSAs as well. Remember, those are my summary ASB link state LSAs that describe reachability to the ASBR. So we see, in essence here, a list of all of the prefixes. Now, granted, this is not a very large database, right? 10 routes, 20 routes, 30 routes, that's certainly not going to be significant enough to cause any concern with regard to the efficiency of OSPF. However, we're demonstrating a concept here, right? And that concept is, how can I make this database more efficient? How can I summarize these prefixes? If you look at the reachability information for each of these particular prefixes here, it's going to be the same. So let's go ahead and do the summary on our ABR. And again, we're going to summarize from an area. So we're going to go into router OSPF 1, and we're going to say area 1 range, because we're summarizing from area 1, 192.168.16.0, 255, 248.0. Now, in our lecture series, we did a calculation on how do we calculate this summary range. But here's a quick way of actually figuring this out. 256 minus 248 is a block of 8. 256 minus 248 is 8. And we're starting at 16. So if we count that, that would be 16, 17, 18, 19, 20, 21, 22, and 23, which means that it's a perfect summary. There's 1, 2, 3, 4, 5, 6, 7, 8 prefixes. So that's kind of a quick way of calculating the summary, is to just simply by calculating essentially the block size, which is essentially just a supernet, as long as the block is divisible by what number you're starting with. So let me rephrase that. As long as the number you're starting with, the prefix or the subnet you're starting with, is evenly divisible by the block size, it is a valid summary. So you couldn't do, for example, 16 with a block of 32, so having maybe a 224 here, or 16 with a block of 64, maybe a 192, 128 here, or 192, excuse me. So as long as the number that you're summarizing, the amount of subnets that you're summarizing is evenly divisible into the number you're starting with, that is a valid summary. So this is a block of 8 starting at 16, 16's inclusive, which means that's going to be our summary. So I hit return. Now, what this does is it does a couple of different things, right? First of all, we're going to see a type 3 LSA, show IP OSPF database, and we are now going to see a LSA type 3 being generated by router 1. Now, in the past, we saw, let me see if I have that here. Well, on router 1, we would not, we didn't run the command prior to doing that, I don't think. Let me go ahead and remove the summary. and show you what this would look like without the summary. So here's all of the individual type 3 LSAs that are being generated, right? Which includes 16, 17, 18, 19, 20, 21, 22, and 23. If I do the summary, and I take a look at that database now, we can see that it's gone down significantly, right? In fact, let's actually look at what's going into area 0, which is right here. Got to make sure you're looking at the right area. These are the type 3 LSAs that are being sent into area 0. So this now is the individual prefix that represents that summary. If I do summary, I can actually see that prefix listed here. Where is it at? Let's do 192.168.16.0. And we can see for that 16.0 that it has a /21 prefix. And it's been updated 4 different times in this particular case. All right. So again, we're summarizing 16 through 23, which reduces the size of the topology database. Now, the other interesting thing here is that this metric is calculated based on the metric of the links, not only the cost to get to that router, which is 10, plus the cost of the individual link. Now, I won't be able to adjust that because of the way that the network is configured. If I go to router 2 and I do a show run interface loopback 0, you can see that these are basically just secondary addresses. So the metric for each of these subnets is essentially the same, which means that the seed metric is going to be the same. But again, with the area range command, section OSPF, with the area range command, it is the area that you're summarizing from, not the area you're summarizing to. All right, that's very important. Now, if I look at the routing table on router 3, we should see, because that's in area 2, show IP route OSPF, we see that 192.168.16 subnet /21, rather than seeing the individual prefixes. Same thing would happen with router 4, show IP route OSPF, we see the 16.0/21. Now, we can't really tell from this perspective whether or not this is a summary. This might be an actual prefix that's being advertised. There's nothing in the route itself that indicates this is a summary. It is a type 3 LSA. We can see that from the OIA, but just because it's a type 3 LSA doesn't mean it actually represents a summary process taking place. If I do a show IP OSPF database, and I take a look at the OSPF database on router 4, I'll see the same type 3 LSA coming in as well. Again, this is from router 4 is in area 0, and this is coming from router 1 is the ABR that's advertising that prefix. There is the sequence number, which corresponded to what we saw with router 1. Remember that the databases within the area have to be the same. That's a very important concept within OSPF. So we see this type 3 LSA for that summarized address block that we had in area 1 that's being advertised into area 0. And the type 3 LSA for the individual networks is now suppressed. So if I shut down one of those, if I had the opportunity to shut down one of those loopback addresses, if they were separate loopbacks, it wouldn't affect the advertisement of the summary unless that particular loopback happened to have the lowest metric, and then the metric might change for the prefix. If I look at the routing table on router 1, it hasn't really changed, right? Because it is the ABR. So as the ABR, it is going to have all of the individual prefixes listed. However, there is one significant change here, and that is this null 0 route that gets added to the database, to the routing information base. That null 0 route, which shows up as an OSPF route, is essentially a bit bucket, right? The purpose of summarization is to reduce the number of prefixes, but what if our summary isn't specific enough to only include prefixes that we actually own? In this particular case, it only includes prefixes that we own, but it is possible that other prefixes might be included because we don't have contiguous blocks of addresses and so on. and those networks might not actually exist within the topology. The null zero route gets created automatically as a loop avoidance mechanism for that particular summary. So if I do a show IP route 192.168.16.0/21, well, I don't need the 21, but we can see that this is a intra-area route, but it's matching over to the null zero interface. All right, it is a /21, right? Actually, this is the wrong one. Let me make sure I'm looking at, it's pulling up this one. I'm not sure that I could put in the prefix. I guess I could do it this way. 248. There we go. And we can see that this is matched to the null zero interface. All right. Now, is that going to be a problem? What if I send a packet to 16.10 or 17.10 or 18.10? Yes, those packets would ultimately match this route because only the first 21 bits are considered in the matching condition. However, as with any kind of routing, we always do longest match routing, meaning that we're going to match the packet to the longest match prefix. /24 for 16.10 would be a better match than the 16.0/21. So let's say, for example, that this 23 subnet didn't exist on the loopback interface. However, that 23 subnet would be included in the summary range. Because the 23 subnet would not be in the RIB, the packet that was destined for 23. whatever would ultimately end up matching the null zero route, which means that it would get dropped. Because ultimately what would happen if we didn't have that null zero route is that the packet could potentially match a default route. And it might get sent to the internet, or it could be sent to another router in our topology, and then because of the summary, it might be sent back, and the route might end up going back and forth. All right, so let's go ahead and move into task number 2. In task number 2, we're going to do summarization on our ASBR. Now, because we're not summarizing from an area in this case, the summary process is slightly different. But we can summarize on an ASBR as well. R3 in this particular case is redistributing external networks and advertising them over to R1 as type 5 external LSAs. And then R1 in turn is going to flood that information across to the backbone and into other regular OSPF areas, but each prefix is going to be sent in. So it is possible to summarize those external networks as well, and that again is the same result. Is it's going to minimize the number of routing table entries, it's going to reduce LSA flooding, it's going to save CPU cycles, CPU resources, and so on, and it's also going to localize the impact of topology changes if one of those external networks were to fail. So R3 is the ASBR in our particular topology. It's redistributing external networks, and since it's the one responsible for originating those individual type 5 LSAs, it's also going to be the one that's going to be responsible for generating the summary for those type 5s. Now we do this under the OSPF process just like we saw on the ABR, but instead of using the area range command, we're going to use the summary address command. And we're going to specify the summary, in this case 10.33.4.0. The mask is going to be 255.255.252.0. 256 minus 252 is 4, so that's a block of 4 starting at 4, which is evenly divisible, so that's possible. And that's going to include networks 4, 5, 6, and 7. So the summary is going to come in as a /22. Just like we saw with the area border router, do show IP route pipe include null zero, we see a null zero route created in this particular case for the exact same reason, right? As a loop avoidance mechanism. Now, we don't have a seed metric in this particular case because these are external prefixes. So the seed metric is going to be basically how do the routes get into OSPF. If I do a show IP route, show IP OSPF database, 10. Let's look at 33.4.0. Let's do external. We can see that this is coming in as a well, it's being summarized now as a /22, but it is coming in as a metric type of 2, and the seed metric is 20. And that's because of the original redistribution command. We redistributed our connected routes with the default behavior, which means redistribute connected subnets without changing the metric type or without changing the seed metric. So the summary is going to essentially assume that same characteristic. If I change my redistribution properties and I change the metric type, let's do a show run, for example, pipe section router, and let's do a redistribute connected subnets, but let's set the metric type to 1, and we'll even set the seed metric to 100. Now if I do a show IP route external, we can see, that's interesting. Let me do a show run pipe section router here. It should have changed, because with the summary address command, I don't have the option of applying those properties to the summary, right? I can say do not advertise this summary, which allows me to kind of suppress external prefixes if I want. Advertise the summary only. Advertise it only if it's part of an NSSA. So if it's coming in as a type 7, or send it in with a tag, but I can't apply a route map. I can't change the metric type. I'm just curious why. And it may not be reflected here, but let me do one more thing. Do show IP OSPF database external 10.33.4.0. Here we go. It just took a little bit of time to take place. So it is coming in as a type 1, and the initial seed metric is 100. So unlike the area range command, where it's really based on the prefixes that are included in the summary, in the case of an external summary, it's based on how the routes are originated into OSPF in the first place. So if I go over to, for example, router 1, and I do a show IP route OSPF, I should see that OE1 route now, and we can see that the metric incremented as it came through the network. All right, they didn't have you do that in the exercise in the ENCOR lab, but still something that I wanted to show you. So show IP route, let's take a look specifically at OSPF. Same thing here, OE1. The metric is a little bit different because we have some additional links in between. All right, and if I do the same thing on router 4, show IP route OSPF, oops, I can see that E1 route. All right, so again, the idea here is that we're trying to reduce the size of the routing table by introducing this summary. The only true restriction of this, though, is that you have to have a good addressing plan, right? You have to have a good hierarchical addressing plan where you have contiguous subnet blocks throughout the network. If you don't have contiguous subnet blocks, it makes it practically impossible to summarize those prefixes. If I take a look at the database on router 4, show IP OSPF database, we're going to see a couple of different entries here. Here's the external prefix. That's the type 5 LSA to reach the external prefix. Here's the type 4 LSA to reach the ASBR, which in this case is router 3. This is being advertised by the ABR, and then I'm going to use my router link states to reach that ABR based on those type 1 LSAs, because that ABR is in the same area. All right. Now, there are some filtering options that we can apply here, and that's what task 3 is. Our final task in this exercise is all about, is how do we apply OSPF filtering? Internal routing protocol filtering does give us a challenge when it comes to link state routing protocols like OSPF. Because as we talked about many times throughout our lecture series, OSPF and link state specifically doesn't advertise routes. They advertise topology information. What I like to say is routing to nodes, not to networks. Also, the SPF loop prevention algorithm relies on all the routers in the same area having the same copy of the link state database in that area. So filtering to change the LSA contents could conceivably make it so that link state database is different on different types of internal routers, and that's going to cause routing irregularities. So we have some limitations on the type of filtering that we can apply in OSPF. Cisco IOS actually supports 4 types of OSPF route filtering. We can do an ABR LSA3 type filtering using a filter list command, where basically we're preventing an ABR from creating certain types of type 3 LSAs. We can use the area range not advertised command to basically, it's just another process that prevents the ABR from creating specific type 3 LSAs. We can do filtering routes, not specifically LSAs, but routes using a distribute list command. But the route filter, we know that a router can filter routes that the SPF process is attempting to add to the routing table. Here's the thing though, unlike EIGRP and or RIP and so on, the other protocols we might apply this to, just because a route is filtered from the routing information base does not mean that it necessarily has to be filtered from the link state database. So we can actually apply filtering to routes and not LSAs, but that would only affect the routing table, not the link state database. We can also do this, by the way, for type 5 and type 3 LSAs. The routing tables don't have to be the same between the routers within an area. The link state database has to be the same between the routers within an area. All right. And the last option is the summary address ASBR summary command with the not advertise to say that we're going to apply the not advertise option to those type 3 external LSAs. All right. So let's start by taking, have a quick discussion, and we'll take a look at applying a filter using prefix lists and the filter list command. Then we'll take a look at applying a filter list to an area. And then we'll take a look at filtering with the area range command. And then we'll take a look at the distribute list command using access list and distribute lists. And then we'll take a look at a prefix list example as well. And then finally, I'll kind of show you the capstone, if you will, a combination of a route map, a prefix list, access list with distribute list to do some interesting filtering in that regard. So we're going to start with some very basic filtering options. In this case, filtering our type 3 LSAs with the filter list command. ABRs don't ever forward type 1 and type 2 LSAs from one area to another. You can't even make the router do that. They create type 3 LSAs for each subnet defined based on the type 1 and type 2 LSAs that might exist. Now, a type 3 LSA doesn't contain detailed information about the topology of the originating area. Instead, each type 3 LSA basically represents the subnet, the cost, and then the ABR that allows us to get to that particular subnet. We've seen this a couple of times as we've gone through and analyzed the database. Now, the OSPF ABR LSA, type 3 LSA filtering feature allows the ABR to filter these type 3 LSAs at the point where the LSAs would normally be generated, right? So by filtering at the ABR before those type 3 LSAs are injected into another area, that means that everybody within that area is going to have an identical link state database inside the area. So that means that we're not causing or creating potentially any kind of problem in this particular case. All right. Now, to configure a type 3 LSA filter, we use the area ID or area number, and then we use the filter list prefix command. We reference the prefix list name, and then we specify inbound or outbound. I know it's a lot of information. We'll go through an example here. We'll take a look at that configuration example. That referenced prefix list is what we use to match the individual networks or the individual subnets and masks that we're actually trying to filter. The area number and the in and out options allow us to specify out of a particular area or into a particular area depending on how it's applied and where it's applied. So on router 1, we're going to go ahead and configure this. This is our ABR. All right, we're going to configure an OSPF filter list. And what I'm trying to prevent in this particular case is the 2.0 subnet from getting advertised out of this particular area. All right. We also have to clear the OSPF process after we apply the filter list as kind of a hard reset in this case of the OSPF process. All right. So we're going to use a prefix list command. And we're going to use the prefix list command to match the individual prefix that we're trying to filter. All right, so let's say IP prefix dash list from _R2, because these routes are coming from R2. And I'm going to say, let's go ahead and deny 2.0/24. Now, because I don't have an operator here, I don't have a GE or an LE, it assumes an exact match. If I'm getting a /24 route from router 2.0, it's going to match this rule. Now, if I don't specify another rule, there's an implicit kind of deny all at the end, so I need to make sure that I allow the remaining prefixes to be able to come in, because there are other prefixes that I want to allow. And I'm going to say permit any prefix. The /0 in this case, we're not matching the default route, because I'm going to go ahead and say LE32. Now, we talked about prefix lists in our lecture series, but again, this means basically the first prefix notation. This /0 no longer represents the mask, it represents the number of bits that have to match in the address. This represents the length of the mask, and LE indicates less than or equal to 32. Then I'm going to go into router OSPF 1, and I'm going to simply say area 1, the area that I'm filtering from, filter list, and then I'm going to make sure I specify prefix from _R2, and let's make sure it is case sensitive, so we want to make sure that we're matching the case, and I'm going to say out. Now, if I had applied this filter and I referenced a prefix list that didn't exist, then the filter would simply not get applied, it wouldn't do anything. So I'm going to clear IP OSPF process, and it's going to reset my adjacencies. And then if I go to router 1 and I say show IP OSPF, and let's just do this for area 1, we can see that in this particular case, there is an area filter applied out of the area. All right, we're also doing our area range command. There's I'm not sure what the 11 represents here. I was going to say there's 11 prefixes, but this only includes 8 prefixes, so I'm not sure what that represents. But maybe 11 prefix. No, it wouldn't be that. But anyway, this is what we're seeing the filter is applied. All right. Now, if I go into the router and I do a show IP route pipe include 2.0, I can see the 2.0 prefix listed in the local routing table. But if I look at the database on router 3, do show IP OSPF database, I can see that 2.0 subnet is not coming in as a type 3 LSA. In fact, if I do a show IP route 192.168.2.0, it'll say the network is not in the table. And we would see the same thing with router 4 as well. Show IP OSPF database. And the 2.0 subnet again is not in area 0. And show IP route 192.168.2.0 is not in the table. All right. So as the ABR, R1 shows that the area filter is being applied out of area 1. The routing table of R1 still has the route in it, but that's because it's an intra-area route, not an inter-area route in the case of area 1. Router 3 and router 4 show that we're no longer advertising that. All right. Now let's go ahead and do this kind of in the opposite direction. Let's go into router 1, config T, router OSPF 1, no area 1, Let's just do this. And let's do an area 0 in this case, filter list, prefix from underscore R2 in. So what's going to be the effect of this configuration? Let's make sure we clear our process. The effect of this configuration is that area 0 will have the filter applied, but area 2 will not. So again, if I do a show IP OSPF, begin area 1, I can see that the filter is applied. Actually, the backbone area is what I'm looking for. So let's actually begin area 0. Actually, let's just begin area here, because it's not area 0, it's area backbone. But we can see that the filter is applied here, but it is not applied to area 1, and it is not applied to area 2. All right, now I still have show IP route, pipe include 2.0. I still have the 2.0 route. We can see that listed there. If I go look at the route, the database of router 3, which is not in area 0, oops, let me do that. We can actually see the 2.0 prefix here, and if I look at the route, I can see the routes in the database, all right, in the routing information base. If I do the same thing on router 4, remember router 4 is in area 0. I don't see the 2.0 subnet here, and I don't see the route in the routing table. So in this particular case, the filter list is applied to filter that type 3 LSA as they're being advertised to area 0 only. R1 still has the 2.0 prefix in its local routing table, again as an intra-area route. We can see R3's OSPF database also has the 2.0 prefix being advertised into area 2 because we didn't apply the filter to area 2. R3 also added the route to its routing table, but R4 no longer receives the 2.0 advertisement and the route doesn't exist. Now another option we have is we have the ability to filter our type 3 LSAs with the area range command. All right, this is the second method in essence that we're going to take a look at that allows us to filter our type 3 LSAs at the ABR using the area range command. We know what the area range command's purpose is, right? The purpose of the area range command is to perform route summarization at the ABR, basically telling the router stop advertising all of the smaller subnets within this particular range of addresses, creating a single type 3 LSA that represents those prefixes, all those smaller subnets, as one large prefix. But if we have the area range command and it includes the not advertised keyword, not only do we suppress the smaller subnets from being advertised, but also the summary route doesn't get advertised as a type 3 LSA either. As a result, the command has essentially the same effect as an area filter list command, with the out keyword filtering the LSAs going out to other areas. All right, so let's take a look at this configuration. We're going to go into router 1, and we're going to say area 2, and let's go ahead and do our range command. Let's say 192.168.3.0, 255.255.255.0 not advertised. So this is an interesting concept because we're not necessarily specifying a prefix, right? We know that the purpose of area range is generally to do a summarization, but the router doesn't really care if it's a summary or not. It just cares of whether or not it's a prefix that's represented in the global routing table, and now we can specify whether or not we're going to suppress that particular prefix. Notice in this case we don't have the in or out option, so this would only apply in the outbound direction. And we're in essence saying the 3.0 prefix from area 2 is going to be filtered at the ABR, and it's not going to go into area 0 or area 1 as a type 3 LSA. All right. We know that the area range command is more commonly used to advertise a range of networks, two other areas, but in this case, because we're using the not advertise option, we're really using the area range command to apply route suppression to our type 3 LSA. So if I go to router 1 in this case, and I say show IP OSPF pipe, let's do a begin area 2, we should see in this particular case that we're not advertising that 3.0 prefix. It's passive in this particular case. It still exists in the routing table. Do show IP route 192.168.3.0 still exists in the routing table, but it's being suppressed from going into the other areas. For example, if I come into router 2 and I do a show IP OSPF database, I don't see the 3.0 subnet listed here. If I do a show IP route 192.168.3.0, the route is not in the routing table. Same thing would happen with router 4, right? We would see it's, again, show IP OSPF database. The 3.0 subnet is not listed as a summary netlink state. Show IP route 192.168.3.0, not in the table. Okay? So that's another option that we have. Maybe a little bit cleaner, a little bit less flexibility with regard to matching prefix lengths, right? Like a prefix list allows us to match not only the prefix but the subnet mask, whereas this particular case, not really, right? But it does perform a similar function, only in the outbound direction. The third option that we have is to go ahead and do some sort of filtering with distribute lists. For OSPF, the distribute list in command filters what ends up in the routing table. And by the way, it only does that on the router where the distribute list command is configured. It does not remove the routes from the link state database for the area routers. All right? The process is pretty straightforward. We basically set up the distribute list command. We can reference an ACL or a prefix list or a route map. But keep in mind, there are some rules that identify how we can use this distribute list command. The distribute list in the inbound direction applies to the results of the SPF calculation, meaning the routes that are installed into the routing table. The distribute list in the outbound direction applies only to redistributed routes, and we could only do that on an ASBR. Because again, the databases have to match on the routers. All right? So in the distribute list outbound option, we're basically just selecting which routes can be advertised based on the scope of redistribution, not just regular OSPF advertisement. Now, the inbound logic does not filter inbound LSAs. It filters routes that SPF chooses to install in its local routing table. All right? So we can use an access list with distribute list, we can use a prefix list with distribute list, or we can do a combination of route maps, prefix lists, access lists, and so on. So let's start by taking a look at an access list with the distribute list command. And we're going to just apply another filter on router 1. In this particular case, we're going to be filtering the 4.0 subnet. And the 4.0 subnet is this loopback on router 4. All right. So I'm going to come in here and I'm going to create an access list. And because it's matching a route, it's a standard access list, 192.168.4.0, 0.0.0.255. All right. Now remember, we need to have our permit any because there's an implicit deny at the end of every access list. And then I go into router OSPF 1 and I just simply say distribute list 1 in. All right, so the access list allows router 1 to learn all the routes except for the 4.0 prefix. And we use the distribute list to apply this in the inbound direction to filter the OSPF routes that are going to be added to the routing table. All right, so if I do a show IP route OSPF, we see all the prefixes except for the 4.0 prefix. But if I do a show IP OSPF database, I can see the 4.0 prefix. It's going to be in area 0. And it would come in, actually we don't see it specifically. I'm on router 1, so it's going to be part of this guy here. So let's do router, and we should see the 4.0 prefix right here. Yeah. So it is still going into the database, but it's not going into the routing table. All right. So if I go to router 1, and there's a couple other ways that we can verify this. If I do a show IP protocols, and let's do section OSPF, and we can see in this particular case, we have an incoming update filter list for all interfaces, which is 1. But like I said, if I go into the database here, show IP OSPF database router 4.4.4.4, I can see the 4.0 prefix is still being advertised into the database. All right. In fact, not only is it being advertised into the database, but it is reachable, right? We're actually saying this is a valid route, but it's being suppressed from being put into the routing table. Show IP route 192.168.4.0 shows that the route is not in the routing table. All right. Now, if I was to look at router 2, and I do a show IP OSPF database summary, and let's go ahead and pull up the 4.0 summary, I can see that we're actually learning that summary network. All right. So even though it's being suppressed locally within that router, it's still being advertised to the other routers. I would see the same thing in router 3. Let's get a copy of this. Put a do. And we see the same thing in router number 3, and so on. All right. So router 2 and router 3 are both receiving this type 3 LSA for the 4.0 prefix, and they're also adding it to the routing table. All right. Now, what if we wanted to accomplish essentially the same process, but instead let's go ahead and apply it with a prefix list. So let's go back to router 1. And in this case, we're going to deny the 4.0 prefix with the prefix list and apply that instead. So IP prefix list R4-loop deny 192.168.4.0/24. Remember, that's going to be an exact match. And then we still have to say permit 0.0.0.0/0 LE32 for the remaining prefixes. Go to router OSPF 1. No distribute list 1N distribute list prefix list R4-loop. Again, make sure that you're referencing one that actually exists, and that's how we can apply the prefix list. Now, whether you decide to use an access list or a prefix list will really be determined based on what kind of flexibility you need for matching the individual prefixes. If you're concerned about just matching the route and not necessarily the prefix length, then an access list should be sufficient. But if you need to match a route, maybe a few routes, maybe the routes that have a subnet mask greater than 24 or less than 28 or whatever it might be, then in that particular case you may decide that you want to use a prefix list to do that, to match that condition. So again, same result in essence. If I come into router 1 and I say show IP protocols, section OSPF, I can see that we've applied this prefix list filter. And if I look at the database, show IP OSPF database router 4.4.4.4, I can see that 4.0 prefix is in the database, but again, it's not going to go into the routing table. Show IP route 192.168.4.0. The network is not in the routing table. Same result on router 2 and router 3. We see it in the database. We should see it in the routing table as well. And on the same thing on router 3, we see it in the database, and we should see it in the routing table as well. All right, so in essence, the same exact result in this particular case. The only difference is we decided to reference a prefix list instead of an access list. So in our final task, task 6 here, we're going to go ahead and kind of pull everything together. We're going to use a route map, we're going to use a prefix list, we're going to use an access list, and then we're going to apply that using a distribute list. So we're going to configure a prefix list on router 4, in this case, to match the two WAN networks. That would be the 12 and the 13 subnets, right? The 12 subnet here and the 13 subnet. And we're going to apply a filter in this particular case. So let's walk through the process here. Let's say, for example, IP prefix list, and I'm going to say WAN links. And I'm going to say, we're going to go ahead and permit 172.16.12.0/ I think that's a 30. Yep, it is. And we're going to also do the 13. All right. Now we're using the permit statement here, which means that the implicit deny at the end will take care of the rest of the routes that we don't want to insert, right? Just like an access list, just like a route map, there's an implicit deny at the end that gets applied. Now we're going to configure an access list that actually matches router 1's router ID. This is an interesting concept. IP access -list standard R1-RD. Let's just call it ID in this case. And we're going to permit 1.1.1.1. Now, the advantage of using a route map for filtering is that it gives us a whole bunch of other flexible options. It gives us a lot of granularity. We can combine things like access lists and prefix lists. We can apply specific rules to the routes as they get injected. All kinds of things. We have a whole bunch of flexibility when it comes to implementing route maps. And we're going to do kind of a deeper dive into route maps later on, especially in our advanced routing course that's part of this particular course. All right, so let's go ahead and set up a route map now. And we'll kind of walk through what the route map is doing in this particular case. We're going to call it just WAN filter. And I'm going to say, let's deny 10. So this is our first clause. And this is our deny clause. So we're going to say match IP address. And we're going to say prefix list WAN links. So it's interesting. The prefix list is matching and permitting those prefixes. But the route map clause is denying those particular prefixes. We're also going to do a match IP route source R1 ID. Now remember, when you have consecutive match statements, it's a logical and, not a logical or. And then I'm going to do my second clause, WAN-filter. And this clause, I'm just going to do a permit 20. And then I'm going to go into router OSPF 1. By the way, that's kind of just like a permit all type of clause. A route map clause that doesn't matches everything. Let me say that again. A route map clause that doesn't match anything specific matches everything. And I'm going to say distribute list route map. Again, make sure that you get the right case and the right name. And I'm going to apply that in. All right. So line 10 or clause 10 in this particular case denies routes that match the WAN links prefix list and in combination the R1 ID. So it's possible, for example, that you might have multiple ABRs that are inserting or injecting routes into the backbone, and you want to control who's advertising those prefixes and so on. Maybe you want to even have more granularity where you can control not only who's advertising them, but how they're advertising them into the backbone. All right. In the case of the match conditions here, because the match conditions are sequential and not linear, not on the same line, they are a logical and, not a logical or, which means both conditions have to match for us to take the action, the deny action. And then clause 20 basically permits all the other routes, which allows router 4 to add all the other type 3 LSA routes into its routing table. The route map is applied to the inbound direction as a distribute list to the overall OSPF process. So if I go into router 4 and I say show IP protocols, if I could type, begin OSPF 1, we can see that we have the route map is applied, WAN filter. Of course, we'd have to do some investigation to identify what the effect of that is. If I look at the show IP OSPF database, and in this case, I'm looking specifically for summary. Let's do section summary. That's not going to work. Let's just, I'll kind of filter it out here. It's not too much information anyway. I know that the 12 and 13 prefixes are going into the database, but they're not going to go into the routing table. Show IP route OSPF, and the 12 and the 13 prefixes are not showing up in the routing table. All right. Now, I said that was the last thing we're going to take a look at. We're actually going to take a look at one last thing, which is a little bit less complicated. It's the idea of using the summary address command with the not advertise option. Just like with the area range command, we can specify not advertise with the type 5 AS external LSAs, which are the ones that are advertised by an ASBR. We can do a similar thing. We can limit the way that those LSAs are generated by controlling, well, we could do it, I guess, by controlling how the routes are redistributed, but we can also do it by using the summary address command. So let's go ahead on router 3 and let's create a new loopback interface, interface loopback 1. We're going to give it an address of 10.33.33.1/24 prefix. Now it's automatically going to be included in the database. Do show IP OSPF database self-originate. And you can see that the 33 subnet's here because we just did redistribute connected. All right. And if I do a go to router 1, which is my ABR, and I do a show IP OSPF database external, I should be able to see that 10.33.33.30 subnet as well. All right. So we know that the route's coming in. All right. And if I did a show IP route 10.33.33.0, I'd see a route for that particular prefix. It's coming in with a metric of 110, external type 1. Remember, we changed that behavior on the ASBR earlier. All right. But what if I want to suppress that route? I simply come into router 3. I go into router OSPF 1, and I say summary address 10.33.33.0, 255.255.255.0, not advertise. Now, there's other ways that you could accomplish this goal, right? You could set up some sort of filter to the redistribution process so that it doesn't show up at all in the OSPF process. This is a specific use case scenario, but the end result is essentially the same. If I go to router 1 and I do show IP OSPF database external 10.33.33.0, we don't see that information anymore. It's being suppressed as a type 5 LSA coming from the ASBR. All right. Again, there's other ways to do this. There's other ways to accomplish this goal. When I did my redistribute connected, I could have applied a prefix list or a filter to that redistribution process, and so on. So there are other things that we can do. But this just kind of covered some of the basics, if you will, of optimizing OSPF through the use of summarization, and then having the ability to apply different filters. And you really have to think, because there are so many ways to affect essentially how information is filtered within OSPF. You have to ideally kind of identify what your overall objective is. And there may be multiple ways to accomplish the goal, but there may also be different side effects to each of those different implementations. So you have to try and pick what is going to fit best in your particular environment. All right. So this was a good demonstration. We're going to go ahead and wrap up this exercise. We got one more brief section to discuss and one more discovery, and then we'll wrap up this lesson altogether. So we'll see you guys in the next discussion about OSPF v3. In this section here, we're talking about the difference between OSPF v2 and OSPF v3. But before I start this discussion, I want to make sure that you guys understand that there are basically two different types of OSPF v3. OSPF v3 traditionally has simply been OSPF for IPv6. And you could run OSPF v3 separately. You can run a dual stack environment where you run v4 and v6, and you just simply configure OSPF v3 very similarly to how you would configure OSPF for IPv4. But there's another type of OSPF v3, which is the address family mode configuration of OSPF, which allows us to combine the combination of OSPF v2 and v3 into one concise configuration, much like you go from classic EIGRP configuration to named mode EIGRP configuration, or address family mode EIGRP configuration. There are some significant differences, though, specifically with how the transport works. In EIGRP, when you're running named mode configuration, you're really just combining the configuration into one concise configuration under address family mode, but you're still running completely separate stacks. So you have multiple EIGRP topology tables, you have multiple EIGRP adjacency tables, and you have multiple routing tables. With OSPF v3 address family mode configuration, you're actually combining the stacks together, creating a single database that contains all of the v4 and v6 information, a single adjacency table, and you're actually using the v6 transport to transport all of the messages back and forth between the routers. So not only are you combining the configuration to make it more efficient, the actual operation is very efficient as well. All right. So we know, excuse me, we know that OSPF v2 is obviously very flexible, a lot of configuration options that we have. The OSPF v3 really just as flexible, and in fact all of the concepts that we learned about in v2 do carry over to OSPF v3 if we're talking about traditional IPv6 for OSPF configuration. Just like with the EIGRP, moving to a different protocol stack does not really change how the protocol operates. There are a couple of different LSA types because of the link local addresses, and we do rename a couple of the different LSA types as well. But for the most part, the protocol operates essentially the same way, meaning that the cost calculations, link state databases, even the commands that we use like distribute lists and filters, implementing OSPF in general, summaries, summary addresses and area range commands, they're all configured basically the same way. Slightly different if you're using address family mode configuration, but pretty much the same if you're just doing traditional OSPF v6. Okay, so we can implement OSPF v3 traditionally, or we can implement OSPF v3 using the address family mode, but again, transport happens differently in that case. So for traditional OSPF v2, router OSPF, put in a process ID, all the traffic is transported over IPv4 independently of whatever might be running in v6. If I did OSPF for v3 for IPv6 only, I would use the command IPv6 router OSPF, put in a process ID. Doesn't have to match because these are independent protocol stacks, and then go ahead and set up the interfaces to run the protocols as well, and all the peering and all the communication occurs with the FE80 link local addresses. OSPF v3 for v6 and v4 address families, meaning that we're now doing kind of this combined configuration using address family mode configuration. We're combining the stacks, right? So everything is transported over IPv6, even the v4 reachability information. We no longer have any traditional v4 peerings. We still can advertise and communicate v4 routes, but we don't have any traditional v4 peerings. All right. So in the traditional OSPF v2 method, using the router OSPF command, IPv4 becomes the transport. If we're implementing OSPF in a traditional IPv6 mode, IPv6 router OSPF. But with OSPF v3 address family, we actually use the global command router OSPF v3, and then we start to do our address family configuration. I'm guessing that in the advanced routing course that we'll probably see this implementation. I think in the lab, they basically just have you doing some classic v3 configurations, which is fine. That's a good place to start. But OSPF v3 is really where you want to be if you're running a dual stack environment. Which of the following commands is used to configure OSPF with address families? Well, we just mentioned that. Router OSPF v3, and we put in a process ID. And then once we go into that mode, then we can set up our IPv4 address family and our IPv6 address family, to take care of everything. All right, everybody, welcome back to our final discovery for OSPF. Discovery 10, we're going to be talking about implementing OSPF v3. Throughout this discovery, we're going to learn how to implement OSPF v3 in our dual stack IPv4 and IPv6 environment. We're going to take a look at classic OSPF v3 configurations versus the address family mode configuration. We're also going to be taking a look at some of the tuning capabilities that we have with OSPF v3 as well. Now, Router 2, Router 3, and Router 4 have already been completely pre-configured with their OSPF configurations. R1 has been pre-configured with all the v4 and v6 addresses, but doesn't actually have any routing protocol configurations on it presently. So on R1, our first task is going to be to configure OSPF v3 for IPv6, but we're going to do that in a traditional way, where we have a dedicated OSPF process that serves the v6 protocol. Then we're going to migrate that configuration to the newest configuration approach, which is a single OSPF v3 process that serves both the v4 and the v6 address families, like we discussed in our lecture portion of this particular topic. All right. Then we're going to go ahead and configure things like default routing in the OSPF v3 domain. We're going to take a look at how we can tune the OSPF v3 interface costs. How do we configure passive interface in this particular case? And how do we advertise an IPv6 summary route? Now, if you look at the topology diagram here, R1 and R4 are connected with a multi-access Ethernet segment. R1 and R2 are connected over a point-to-point serial link, and R1 and R3 are connected over an Ethernet WAN link. So the discovery is basically prepared with the devices that are listed in this particular topology, but like I said, all the v4 addresses, v6 addresses, and so on are configured. So our task is basically to focus on R1. We're going to enable the traditional OSPF v3 configuration on R1. Then we're going to migrate that OSPF v3 configuration to the more modern OSPF v3 address family configuration. And then finally, we'll take a look at how to optimize that configuration as part of the process. All right. So the first task would be, in this particular case, would be to go ahead and enable IPv6 routing. Because IPv6 routing is not enabled by default, we have to do that, and we use the IPv6 unicast routing command. Then we're going to have to enable the OSPF v3 routing process using the process ID command. So it's going to be IPv6 router OSPF process ID. And this is what allows us to enable OSPF for the IPv6 process in router configuration mode. The process ID is still an internal identification. It is locally assigned, and it is a positive integer, as always, from 1 to 65,535. Because it is for IPv6, it's completely independent of the IPv4 routing process. We additionally could specify the router ID. The router ID is still a 32-bit dotted decimal address. It could be selected from one of our active Ethernet interfaces or loopback interfaces that have a v4 address, but because we are running v6, we want to have a consistent router ID, and we can set that manually. All right. Then we enable OSPF v3, but not with network statements. In IPv6, the routing process is always enabled explicitly on the interface. So we use the IPv6 OSPF process ID area ID command to do that, and that assigns that interface to the OSPF process and puts it into an area. And we'll talk a little bit more about that as we start to go through the process of configuration. Then we can also do our passive interface configuration. So let's start with task number 1, which is to go into router 1. Let me just do a quick show IP interface brief. Yep, all my interfaces are operational. And the first thing I'm going to do is IPv6 unicast routing. All right, OSPF v3 is the IPv6 capable version of OSPF. It's essentially a rewrite, if you will, of the OSPF protocol to support IPv6. Most of the foundational elements remain the same as they have in IPv4, or what we would traditionally call OSPF v2. The OSPF v3 metric is still based on interface cost. The overall path cost is calculated the same way. Most of the LSA types are going to be same. There are some additional LSA types that are created, as well as some LSAs that are renamed. The packet types, the neighbor discovery mechanisms, they're going to be the same in OSPF v3, and so on. We have the same interface types as well, things like broadcast, point-to-multipoint, point-to-multipoint non-broadcast, non-broadcast multi-access, loopback, virtual links, etc. All right, so let's go ahead and enable the routing process. We use the IPv6 router OSPF, and then we specify the process ID, and then we can specify our router ID. Again, not because this is a dual stacked environment, not necessary, because the v6 process will use one of our v4 interfaces to establish the router ID. But if this was a v6 only process, then the OSPF process would not operate, right? So for OSPF for IPv6, it doesn't require an IPv4 address for the router ID, but it still does require a 32-bit number to be set. And we define the router ID by using that router ID command. Again, if we don't specify it, it'll try to dynamically choose the highest active IPv4 address on a loopback interface. And if there are no loopback interfaces, the highest active IPv4 address on a physical interface. All that being said, if there are no active v4 addresses or v4 interfaces on the router, the process is going to fail to start in this particular case. All right. Now, passive interface is implemented essentially the same way. We'll make loopback 0 passive in this particular case, just to demonstrate the syntax. But it's the same effect, right, that essentially suppresses the protocol from running on the interface, but still allows the network to be advertised. All right. So in the IPv6 OSPF configuration mode, we can do things like passive interface. We would enable summarization. We could fine-tune the operation of OSPF. But like I said, we don't use network statements to enable the process to enable the OSPF process on specific interfaces. In fact, with any IPv6 configuration, there are no network commands. So to activate the OSPF process on a particular interface, we need to use the IPv6 OSPF command in interface configuration mode to enable that process. Now, on router 1, we want to enable OSPF for IPv6 on all of our interfaces except for the interfaces that aren't being used in the topology, and we certainly don't want to enable it on our loopback 1 because that's our internet-facing interface. So interface loopback 0 is going to go into area 0. Ethernet 1.0, the 14.0 subnet, that's going to go into area 0. Serial 2/0 is going to go into area 1. And Ethernet 1.1 is going to go into area 2. Additionally, we're going to go ahead and assign the network type on our loopback as point-to-point. All right, so just like we saw with IPv4, by default, OSPF for IPv6 is going to advertise loopback networks as a host route. So in this case, it would advertise it as a /128, and we don't want that to take place. There's a prefix on there, 2001. Let's do a quick show IPv6 interface brief, and we can see the 2001 prefix on our loopback interface. This is the prefix that we want to make sure is advertised as a /32. Now let's go ahead and take a look at the OSPF v3 adjacency, and we're also going to take a look at the routing table on router 1. So let's do a show IPv6 OSPF neighbor. And we can see we have three adjacencies here. Router 4 with a full adjacency. Router 4 is the actual DR in this particular case. We also have an adjacency with router 2 with a priority of 0 because, again, that is a point-to-point serial link. And then we also see an adjacency with router 3. Router 3 is the DR in this particular case as well. Let's also do a show IPv6 route OSPF. And one of the things I want to point out here is the intra-area routes that's listed right here. We see OSPF intra-area routes, and certainly we see all of those different prefixes. But we're not seeing, well, the router 1 is the ABR in this particular case, right? So it is participating in each of those areas individually. So we do see all of these prefixes. So after enabling OSPF on the OSPF process, I should say, on our IPv6 interface, we verify those adjacencies just like we did with IPv4. We can selectively display the OSPF portion of the routing table. We can see all the routes here, and essentially we're seeing basically the same thing. Now remember, R1, from R1's perspective, it appears as though all of the routes are intra-area routes. That's because it is connected to all of the areas. Ethernet 1.0 is in area 0, Serial 2.0 is in area 1, Ethernet 1.1 is in area 2, and so on. All right. Now, one of the other things that you'll notice here are the link local addresses. These are not EUI64 link local addresses. These are statically assigned link local addresses. Router 1 is FE80:1, router 2 is FE80:2, router 3 is FE80:3, router 4 is FE80:4. In fact, if I do a show IPv6 interface brief, you can see that we have the same link local address assigned on every interface, minus the loopbacks here. But on our Ethernet interfaces, we have the same link local address. This is actually a good approach because it provides consistent configuration. And when we're trying to verify OSPF operations and we're trying to troubleshoot OSPF operations, it certainly makes our life much simpler because we have a common link local address that we can easily recognize and document. If we're using the EUI64 process, it might be more challenging because we're going to see these long EUI64 addresses that represent the link local addresses in this particular case. All right. So, and is there a problem with these link local addresses being the same? The answer is no, because link local addresses are non-routable, which means they're only significant on the wire itself. They, of course, have to be unique between the routers that share a common segment, but they can be the same within the router. All right, so let's go ahead and examine the OSPF database here, specifically for IPv6 in this case. Show IPv6 OSPF database. And what I want to point out here is one of those concepts that I mentioned briefly in the introduction of this lesson, which is one of the renamed LSA types. Inter-area prefix link states, these are my type 3 LSAs. They describe essentially the same thing, right? The format of the database is slightly different, but we can see the advertising router is the ABR, and then these are the different individual type 3 LSAs that are being generated by the router. In addition, we have these type 8 LSAs, and we have what we call intra-area prefix link states, which are additional LSA types that are defined with IPv6. right? OSPF v3, which is OSPF for IPv6, it renames a couple of different LSA types, and then it also defines 2 additional LSA types that we would never see in OSPF v2 for IPv4, all right? Now, the 2 different renamed LSA types are our type 3s and our type 4s. Type 3 would be our inter-area prefix LSA. These are my type 3 LSAs that get advertised, and they represent internal networks to routers in other areas. So basically those OIA routes, the inter-area routes. The type 3 LSAs could represent a single prefix, or if we are in fact doing summarization, they could represent a set of summarized prefixes. And again, only our area border routers generate these type 3 LSAs. In OSPF for IPv6, addresses for these LSAs are expressed in the format of IPv6 prefix and then prefix length instead of address and mask like we would see in IPv4. And if it is a default route, that's going to be simply represented with a prefix length of 0 with a double colon as the network address. The second type that was renamed is our type 4 LSA, and these are now called inter-area router LSAs. Remember, the type 4 LSAs allow us to identify an ASBR outside of our area. So any type of ABR that is attached to an area that has an ASBR attached to it will start to generate type 4 LSAs to advertise the location of the ASBR. The ABR, like I said, is the one that's going to originate these inter-area router LSAs into the areas to advertise ASBR reachability outside of the area that the ASBR is attached to. All right, and we're going to generate separate inter-area router LSAs for each individual ASBR that I'm going to be advertising, right? So I could have multiple ASBRs within an area, or I could have multiple ASBRs across multiple areas. I'm going to use a type 4 inter-area router LSA for each of those. Routers that are trying to reach external networks, they're going to use those type 4 LSAs to determine the best path to the ASBR. And then, of course, the type 5s or the type 7s are what we use to identify the external prefixes themselves. There are 2 new LSA types, link LSAs, which are type 8. These link LSAs have a link local scope flooding, meaning that they're never flooded beyond the broadcast domain, if you will, from which they're associated to, because these provide reachability information for our link local addresses to the other routers that share that common broadcast domain. So they basically inform the other routers that they're attached to the list of IPv6 prefixes that are associated to the link. And then they'll also allow the router to assert, if you will, a collection of option bits that are also associated with the network LSAs that are going to be originated for that particular link. All right. Another type is what we call an intra-area prefix LSA, or type 9. Intra-area prefix link states right here. These get originated, and we can actually originate, we can see that router 4 is doing this in this case, multiple intra-area prefix LSAs for our transit networks. Each of them are going to have their own unique link state ID. The link state ID for each of these intra-area prefix LSA basically it identifies its association to either a router LSA or some sort of network LSA. All right, this is going to allow us to identify things like stub prefixes for stub networks, as well as our transit networks. So, but we still have kind of our standard LSAs here. Here's my type 1 LSA. Here's my type 2 LSAs. These are my type 3 LSAs. These are my type 8s. These are my type 9s. We don't have an ASBR in this particular case. Or else we would see those type 4s as well, the inter-area router LSAs. So we're going to move on to the next task. Task number 2 in this case is migrating to OSPF v3 address families on router 1. All right, OSPF v3 doesn't only support the exchange of v6 routes. It actually uses the same transport mechanism to exchange IPv4 routes. So we can actually enable a single process that supports both v4 and v6. Now this is not like the named mode configuration that we see with EIGRP, where we still have kind of separate processes that are running. In this particular case, we're actually using the v6 transport to exchange v4 reachability information. So that's actually a pretty significant difference, because we don't have two separate neighbor tables, we don't have two separate topology databases. We still have our separate routing tables, but as far as the actual data structures that are used for OSPF, we have a single data structure, right? So that single database is going to have the LSAs for v4 and v6. The adjacencies are only are going to be established for each address family, and then we have specific settings that we can apply and configure for each address family as well. The OSPF v3 address family feature was introduced in iOS 15 code. I believe it was 15.2.1t and 15.1.3s. Don't quote me on that, but I believe that's correct based on the documentation, right? So the newest OSPF v3 configuration uses a single OSPF v3 process. Like I said, it's capable now of supporting our v4 and v6 within a single OSPF v3 process. It builds a single database with LSAs that carry that information and so on. So running a single OSPF v3 process is very, very useful in this particular case. Now, we don't have to remove our old configuration to start this configuration. We're simply going to say router OSPF v3, put in the process ID, we can specify our router ID, and we can still do our passive interface for loopback 0, all right? So we enable this process by simply typing router OSPF v3, and then we specify the process number. All right, now within the OSPF process configuration, we can set all the other parameters. We have lots and lots of different parameters that we can set, which you should be relatively familiar with, because again, the overall structure of the protocol doesn't really change if you're running OSPF v3. It's just how the information is exchanged between peers. So if we take a look at the resulting configuration, we do a show run section router, and we can see actually that there are a couple of things that are done, right? Here's the syntax that we executed, and then it automatically created the IPv6 address family, right? That was created on router 1. Basically what happened is the Cisco iOS parsed the previous OSPF v3 configuration, and it found the OSPF process was only enabled for IPv6 in this case. So when we went to the new configuration, the IPv6 address family was instantiated, and the IPv4 address family doesn't have any configuration because we didn't have any v4 specific configurations. The passive interface goes under the v6 address family, and so on, right? So it was a very easy transition, if you will, to OSPF v3. Now let's take a look at how we look at some of these outputs, because the syntax here is a little bit different than what we're used to. So instead of doing, say, show IPv6 OSPF neighbor, we would actually come in here and we would say show OSPF v3 neighbor. All right. Now, if you look at this, it's slightly different, although it shows us essentially the exact same information. This is the traditional v6 OSPF v3, and this is the address family. You can see the difference there. Basically, it's address family IPv6. We don't see that listed here. We see the process ID. We see the router ID. So even though we're running the new version, if you will, of OSPF v3 address family mode, we're still actually running the old mode as well. If I do a show run pipe include OSPF, we can see that we do have those traditional IPv6 OSPF commands on the interface, but we don't have show run pipe section router. What we don't have is we don't have this replaced the traditional IPv6 OSPF router OSPF command that we entered to do classic configuration. Now, if we take a look at the database, show OSPF v3 database, we can see the database is identical, right? The only difference, as far as the LSA types, it's identical. The only difference is we see address family information. So if I did have some v4 information, I would see that listed here as well. Certainly we're seeing a bunch of v4 related addresses here, but keep in mind, those are router IDs. Router IDs are always going to be listed in a dotted decimal format. All right. Now we can still verify OSPF v3 with our old commands. Show IPv6 OSPF neighbor, show IPv6 OSPF database. I kind of demonstrated that. Or we could do a show OSPF v3 neighbor or show OSPF v3 database. Because, or actually, even though we changed to OSPF v3 configuration, the new approach, the connectivity was retained. We didn't reset our adjacency and go back in and form a new adjacency. That information was already retained, right? In fact, R1 kind of has a mixed configuration, right? New style as well as old style. Some of the old commands are the interface specific commands. So for example, show run interface loopback 0. We see the IPv6 OSPF network point to point. We see the IPv6 OSPF 1 area 0 command and so on. So in order to enable OSPF v3 on all of our interfaces, we're going to go ahead and modify our configuration slightly here. We're going to go into interface loopback 0 and say OSPF v3 1 IPv6. And we're going to put that into area 0. And we're going to go, we're also going to change the network type, OSPF v3 1 IPv6 network point to point. And then we're going to go into Ethernet 1.0 and do the same thing in area 0. We're going to go into Ethernet interface serial 2.0, sorry. And we're going to put that guy into area 1. And then we're going to go into interface Ethernet 1.1. And we're going to put that guy into area 2. Now, if I do a show run interface loopback 0, you will notice that that did replace the old configuration. We didn't have to remove the old configuration. It replaced the old configuration automatically. All right. Now, the preferred interface mode commands would be the OSPF v3 commands, but the reason why this is important is because we can actually selectively activate the OSPF v3 process on any interface that we want. It's not kind of an all or nothing configuration, right? So we can migrate. You also notice as we were doing that migration, we didn't lose any of our connectivity as we were migrating that. So with this OSPF v3 address family feature, we could have possibly 2 device processes per interface, but only one of those processes is per address family. If the IPv4 address family is used, an IPv4 address would have to be configured on the interface first. For the IPv6 address family, we just simply have to enable IPv6 on the interface because, again, OSPF uses that link local address to form adjacencies and so on. All right? So, again, we didn't have to remove the old configuration. The old configuration was automatically replaced when we started to create the new style configuration commands. All right? The adjacencies, the database, the routing table functionality, it's all remained the same. All right? So now we want to go ahead and enable OSPF v3 for IPv4. We also want to make our loopback 0 interface passive. So I'm going to go to router OSPF v3 and process ID 1. And then we're just going to simply say address family IPv4 unicast. We're going to say passive interface loopback 0. We'll go into interface loopback 0, and we're going to say OSPF v3 1 IPv4 area 0. We'll go OSPF. Not typing well for some reason today. Interface Ethernet 1.0, that's going to be the same. We can see we're starting to form our adjacencies. Interface Ethernet 1.1, that's going to go into area 2. And interface serial 2.0, that's going to go into area 1. So we're seeing our adjacencies form. And by the way, we still have the same states, the down, the init, the two-way, the extart, the exchange, the loading, the full, and so on. None of that has changed. All right. This way, by the way, doing this configuration, some or all of the links could be allowed to do v4 forwarding, and they're configured with v4 addresses. So, for example, we might have pockets of IPv4 only devices that exist around the edge running v4 static or dynamic protocols. So we could forward v4 and v6 traffic between those pockets. The transit devices need both v4 and v6, those dual stacks, if you will, for that forwarding. So this feature, this configuration option, allows us to separate topologies to be constructed for the v4 address family. It installs IPv4 routes in the IPv4 rib, and then the forwarding occurs natively as part of the process, right? The OSPF v3 process supports AF topologies for IPv4. We can do route redistribution to and from any other IPv4 protocol in this case, and so on. All right, so we have the ability now to configure v4 and v6 using the separate address family or AF configuration options. Once we've selected the address family process, we can enable multiple instances on a link. We can enable specific address family commands and so on. So in our particular case, loopback 0 is configured as a passive interface, just like we saw with IPv6. So do show OSPF v3 neighbor, and we can see our neighbors just like we saw for IPv4. Now, because I didn't specify the stack in this particular case, it will show me my v4 neighbors, and then it will show me my v6 neighbors. So this is a nice, clean way of verifying both protocol stacks essentially with the single command. All right, we can also monitor the routing table in the same way, although we would have to specify IP or IPv6. Do show IP route OSPF v3, and we can see our v3 or OSPF routing table for IPv4. All right. Again, the OSPF v3 keyword filters, that in this particular case is filtering out the specific routing table to display those OSPF v3 routes. I can also take a look at the database. So I could do a show OSPF v3 database inter-area show OSPF v3 database inter-area prefix. Oh, I forgot the T. That's why my tab wasn't working. There we go. And we can see, again, it will list the information for IPv4, and then it'll list the information for IPv6. If I scroll down here, here's the IPv6 information. So again, the database is just a single database that contains all of that v4 and v6 information. All right? So we have a single database, all the different LSA types, all my v4 related information, my v6 related information gets mixed together, and then we can examine the specific LSAs as needed based on what we're trying to look at. All right. Now in this case, if I do a show IP OSPF database, we don't see any information because we've moved over completely to the OSPF v3 address family configuration mode. All right. So the next task that we're going to take a look at, actually really the final task in this exercise, is how do we optimize the behavior? Again, all the theory that we've learned, all the concepts that we've learned about OSPF remain the same in this particular case. We just do our configurations slightly differently, right? So for example, if I want to do a summarization on our area border router, I go into config T, router OSPF v3, process ID, address family IPv6, because I'm going to do an IPv6 summary, and we're going to be summarizing these prefixes here. Actually, we're going to create a summary for these. I believe are missing some. No, those are correct. Trying to think of which prefixes we're actually going to be summarizing. It doesn't really matter in this case. I guess we could summarize those, but well, yeah. Let's actually take a look at summarizing those prefixes. Again, the configuration is going to be pretty much the same, right? For example, I would do an area range command if I'm doing a summary on an ABR. I would do a summary prefix command, not a summary address command, but a summary prefix command. Let me just do an example here. So I could say area 1 range, for example, 2001 DB8 ACAD /60 as an example. Or if this router happened to be an ABR, 2001 DB8, we actually do have a prefix here, but it's only a single prefix. So let me just do an example. I would do the summary prefix command if I wanted to create a summary based on an individual prefix. Remember, these would be external routes that are being summarized. I can also do things like a default information originate if I wanted to, and we have the same options. Always, metric type, route map, and so on. All right. So if we were to take a look at the routing tables on router 3 and router 4, let's do a show IPv6 route OSPF. We can see that we have a bunch of inter-area routes. They don't get listed here as OIA, they get listed as OI, but these are my inter-area routes. And obviously we'd want to go ahead and reduce the size of that routing table. Same thing with router 4. Show IPv6 route OSPF. We can see we have a whole bunch of inter-area routes. So when we look at the routing table, there's lots and lots of prefixes here. We can reduce the size of these routing tables by summarizing those inter-area routes at the ABR. So for example, all of those prefixes that we have on router 2, these could be summarized into 1/60 block, right? Because if you look at this address here, the first 16 bits match, then 48 bits, then 32 bits, then 48 bits, and then in essence, the next 8 bits match in this particular case. In fact, actually there's a leading 0 here, so we have to keep that in mind. So it would actually be the first 12 bits that match, and 48 plus 12 is 60, right? So basically the first 60 bits match in this prefix. So what I could do in this case is I could come into router 1. I should go ahead and remove those other commands because they're really not valid. Not that they're going to do anything because there are no prefixes that match those summaries that I created. But I could do area 1 range, and I could specify 2001 DB8 0220 /60. Summarization in IPv6 is done exactly the same way as it's done in IPv4, meaning that we basically find the common bits, that becomes the prefix length, and whatever the value of those common bits are is the network ID. All right, so we can summarize those routes. Now if I go to router 3 and I do my show IPv6 route, we can see that it's a much smaller database. Same thing with router 4, show IPv6 route, a much smaller database. In addition, we go back to router 1, do show IPv6 route. We are still going to see that null 0 route. Let me find it. Connected. Where the heck is it? Probably haven't gotten to it yet. That's the null 0 for our multicast group. And let me try this. I don't know if this will work. Section null 0. Yeah, it didn't show it, but it should be an OSPF route. I'm just not seeing it here, but it's definitely going to be here. Whenever I generate a summary, I always generate a null 0 route right here. There it is. All right, so that's that null 0 route that was generated with a metric of 65. Again, the same rules apply, right? The seed metric is going to be the best metric for the routes that are included as part of the summary. In this case, the metric is 75. If I go to router 4, for example, from router 4's perspective, if I go to router 4 and I do a show IPv6 route 2001 db8 022 /64, I can see that we have a metric of 75 for that prefix. All right. Now, this is not the summary, right? I could look at the summary 220 in this case /60, but it's going to have the same metric in essence because it's coming from the same the same source, right? It's coming from router 1 in this particular case. Now, again, cost is a representation of bandwidth in OSPF. Doesn't matter that we're running OSPF v3, cost is still a representation of the bandwidth. All right. Ethernet is going to have a cost of 10 because the reference bandwidth is 10 to the power of 8 or 100 megabits per second, plus the cost of the serial link, which in this case would be 64. That's what's giving us an overall path cost of 75. Now I can modify this configuration. I could go into router 1, for example, and go into interface serial 20, and I would simply say OSPF v3 1 IPv6 cost 200. This allows me to modify the cost for that particular destination and for that address family only, because the interface cost is applied to the address family, not the interface as a whole. So I could actually manipulate and modify the cost values on a per interface or per address family basis in this particular case. So if we go to router 4 and we verify that change, I come into router 4, show IPv6 route 2001 db8 :0:22/64. We can see the metric is now 211, which is 10 plus the 200 that we specified, plus the cost of the loopback, which is 1 in this particular case. All right, to advertise the default route, like I said, we can go into router OSPF. Let's do this on router 1 since we're kind of making all these changes on router 1 anyway. Let's go into router OSPF v3.1 and address family IPv4 unicast, or well, we'll do IPv6 first. We would do default information originate, and we could do that for address family IPv4 unicast as well, and it would still be the default information originate. And of course all the options would still apply in this particular case with regard to establishing a metric, the metric type, and so on. If I now go and do my show IPv6 route OSPF v3, I can see show IP route, sorry, OSPF v3. I can see that I now have a gateway of last resort that points to router 1 in this particular case. All right. If I do a show IPv6 route OSPF, I can also see that default route listed here. The next hop is the link local address of router 1. All right, so I should actually now be able to ping, oops, I should be able to ping that external v4 prefix 165.201.1. Yep. And I can reach that destination. I should also be able to ping the external v6 prefix 2001 db8 209:165:1, and I can ping that external prefix as well. Okay. So the last thing we'll do is we'll just take a look at the hello and dead timers on router 4. Router 4 is in a multi-access network. So we'll do show OSPF v3, interface Ethernet 1.0, and we should see that essentially everything is the same, right? The priority for the interface is defaulted to 1. The DR and BDRs are elected based on highest router ID because priorities are the same. The cost of the interface is 10. The network type is broadcast, and the hello and dead timers are 10 and 40 respectively, right? And we would see that for both of the Ethernet interfaces in this particular case. The OSPF v3 doesn't change how OSPF runs. They're going to be identical to what we learned with regard to OSPF in general, right? The timers have to match, area IDs have to match, MTU has to match. All the things that we learned about in our previous OSPF lessons still apply with OSPF v3, okay? So we're going to wrap up this discussion. We're going to move on to BGP. We'll summarize this topic in this module, and then we're going to move on to BGP. So we'll see you guys in the next lesson. So in the summary challenge, which two options play key roles in route summarization? This is from the chapter, but network numbers in areas should be assigned contiguously. Where's my mouse? There it is. And VLSM, variable length subnet masking. Which statement correctly describes OSPF summarization? With route summarization, only the summarized routes are propagated into the backbone. With route summarization, all subnet routes are propagated into the backbone. With route summarization, only the default route is propagated into the backbone. And with route summarization, only the summarized routes are propagated into stub areas. So we haven't talked about special area types. Stub areas do allow summaries, but so does the backbone. All right, so in this case, the answer would probably just be A. Assuming that you haven't applied any kind of special filters or you're not doing a not advertise, yes, whatever summarized gets sent into the backbone. It also would be sent into any other area that ABR might be attached to. Which command is used to apply a distribute list to OSPF? Pay attention to the prompt here. Certainly they would have open parentheses as well, but we apply distribute lists under the routing process. It can be applied inbound or outbound. There's no problem with that, but it's not applied in global configuration mode because it applies specifically to the routing process. And it's not applied to a named ACL. A prefix list can filter on which of the following options? Prefix and prefix length. Absolutely. Which statement correctly defines one major difference between route maps and access lists? Route maps can use the set commands to modify the packet header. No. We do have set commands, but we're not modifying the packet header. We're modifying the packet behavior, right? We're either saying override the routing policy or set a metric in the payload or, in the advertised route or set the next hop. But we're not actually modifying the packet header. The packet header stays the same. Access lists can use a match and set command. We know that that's not true. Route maps can use a forward command to route a packet. Nope. Route maps can use the set commands to modify the packet route. Yes, so we could say match IP address and then reference an ACL that matches a particular protocol or a particular data flow, and then we can say set IP next hop or set next hop set interface, whatever. There's a whole bunch of different options that you can do. So we're not specifically modifying the packet header. We're just modifying how the packet is being processed. Okay. Now with QS policies, you could potentially modify the packet header in a sense that you would be modifying maybe markings on a packet, like you're classifying traffic, and then in a QoS policy map, you might be changing the markings of a packet. And you could reference that from a route map, but typically they're separate. Network administrators use the route map tool for many purposes. Which three of the following options are the most common? Not mapping the network. Route filtering, certainly with redistribution. BGP policy attributes, absolutely. Asynchronization, no. Policy-based routing, absolutely, right? Those three make sense. What are the 3 steps in creating the route map? Create a profile, name the route map, add a match statement, add the action. So these 3 steps apply, but they're not necessarily required. You don't necessarily have to do a set action. You don't necessarily have to do a match action, but you could if you wanted to. Okay? And the rest are the duplicate ones, I believe. Yep. All right, so that concludes that lesson. We'll see you guys in the next one.